before getting on a flight myself, and she said, I'm never coming back. No. So I work on data plane problems, and that's my comfort zone. I work on the optimization of the data plane on microprocessors, and I've been working on DPDK for 8 or 9 years, always as a lurker. You know, I'm always somewhere in the background and messing with some code. Yeah, over the last year, 18 months, I've been playing a lot with DPP. So today I'm going to talk about both DPDK and VPP and containers, because the scaling story is becoming important. For DPDK, when it was designed to consume all the cores it was given. It makes assumptions about memory utilization. It makes assumptions it's going to have physically contiguous memory. It makes assumptions it's going to have large blocks of memory. It makes assumptions it's not sharing cores with other applications. Whereas, you know, we look at where the future is going to microservices model, we'll have to move to a much more, let's say, friendlier model where we share those resources with our applications. And that's what I'm going to talk a little bit about today, how we make that happen. And I'm going to talk about it in the context of both DPDK and VPP. Now, last time I tried to talk about DPDK and VPP in the same presentation. I learned the hard way that saying DPDK and FDIO VPP in one sentence at the same time is exceptionally hard. So if something doesn't make sense at any time, if I'm referring to DPDK and it's not clear if I'm also referring to VPP, you know, stop me, because I do better when it's an interactive session. So please stop me, ask questions. It'll make for a much more interesting session. So what I'm going to talk about today, I'm going to talk about why containers and the challenges of containers. I'm going to introduce FDIO VPP. I've already, from talking to people outside in the lobby, I know there's a lot of people who are already familiar with FDIO and VPP, but there are also some of you who aren't. So I'm going to talk, I have 2 or 3 slides introducing FDIO VPP. I'm then going to talk about the challenges of scaling the container data plane for both virtual network functions and then also for virtual switching, and that is for both VNF and NFV use cases. And I'm going to talk about a couple of different approaches for virtual switching. And then I'm going to do a short presentation to show, hey, containers and VPP is really easy, and hopefully that won't explode as any demonstration. I don't know if anybody has done live presentations in the past. I've done buckets of them over the years, and one thing you can be guaranteed without fail is that it'll work a million times until you're standing up there presenting it, and then it'll all fall apart, as inevitably happens, but we'll give it a try anyway. So, why containers and the challenges of containers? So I borrowed this slide from AT&T because I really liked it. And what it shows is AT&T presented this in OpenStack in Boston. And it shows the evolution of their network over time. It shows their enterprise IT workloads today are containerized, and many of them are microservices. And then they have a small number of VMs servicing enterprise workloads. And then what we can see is from today, 2017, through 2018, 2019, we can see that the number of VMs really drastically reduces and the number of containers grows. And we can also see that the virtual network functions, those packet processing applications that they have in their network today are based on virtual machines. But they expect that over time, the number of virtual machines, again, to shrink and the number of containers are growing. So for many, many expect that 2018 is going to be an inflection point for containers and virtualization. So where we've seen in the telecom network. So to date, we've seen many discrete appliances get turned into virtual machines. what we will see in 2018 is many of those virtual machines turning into containers. Now, where it goes beyond that, it may just stop there. We may just see packaging change. We may see applications that were previously packaged as virtual machines get packaged as containers. But the actual architecture of the application not change dramatically. So the actual decomposition of those applications into microservices is a separate step. So this might be, this step between 2017 to 2018 to 2019 may just be a change in packaging for an existing application. Something that was previously wrapped up in a virtual machine gets wrapped up in a container. But the application's architecture doesn't change dramatically. It then is an additional step to take that application and to decompose it into a series of microservices and deploy those in the containers. And we'll talk about that. I'll talk about that a little bit more in depth in a couple of slides later. But it's important to understand that there's two trends going on here. There is both a trend away from virtual machines to containers, but then there's also a second trend, which is a decomposition of VNFs into microservices. Does it make sense to everybody? I see nodding heads. By the way, it's my bad habit to walk around the stage. Am I driving the AV guy crazy? No, I'm all good. That's okay. Now, the other reason, I had a slide here and they made me take it out. And I was at FOSDEM in Belgium. Anybody who's around open source as long as I am will know FOSDEM. Anybody been to FOSDEM? I'm in the west coast of the US, so I know it's a long way away from here. No, the AB guy is way spread. So FOSDEM, if you ever get a chance, it's a free conference in Belgium. And it's incredible fun. I mean, it's great fun. You don't have to pay anything to go to the conference. You just register. It's all sponsored. All the things are sponsored. But the actual conference is run in very much by a team of volunteers. So you end up people bringing their kids to the conference. So you'll have people bringing their teenagers who are just getting interested in technologies. You also have people who can't find babysitter also bringing their kids to the conference. But the amazing fun thing about it as well is that there's bars at the conference, so you have people walk into the lecture halls with a beer in their hand as well. So it's a very informal, fun conference, and it's been on the go for a long time, and it's great fun. I've been to it. I've been lucky enough to go. So it's not a big trip for me. I've been lucky to go to it several times. It's been enormous fun. I tried to get into the containers room. I tried to get into the containers, Kubernetes, and microservices room. I had to wait outside the door for an hour, and eventually, when I got in, there was people sitting two to a chair. People sitting down the front, people sitting everywhere, guys hanging out of the ceiling. Because that's how hot the technology is at the moment, and that's how interested people are in microservices and containers. And I think that also is a factor at play here, is that many people, some users are looking at those applications that were that came from discrete boxes, are maybe getting deployed as VNFs, and looking at the benefits of microservices, both the robustness and the scalability, and saying, okay, how can I take my application, how can I take my VNF and realize those same kind of benefits? Okay. So I think I made the point already pretty well that just because containers doesn't equal microservices, so you can change the packaging to be from a virtual machine to container packaging, but it doesn't necessarily mean that it's a microservices. The decomposition into microservices is another step, and it's another trend entirely. But when people think about containers, they think about microservice-like behaviors. I like this from Peter Willis, where he said operators, that's network operators, will have to start, Peter Willis, sorry, is the chief researcher for converged networking at BT, British Telecom in the UK. So the operators will have to start treating their network functions less like pets and more like cattle. So the analogy is that pets are like the VMs. They're relative, I have a few of them and I know where they are most of the time. To where those VMs, those pets become more like cattle in that I have very large numbers of them. and their life cycle is very short. You know, I spin them up and I tear them out and I don't even think about them. So when people think about microservice-like behaviors, what do they expect? Well, they expect decomposition. They expect something that's relatively modular. They expect it to be relatively stateless, or to indeed have minimal state. The more state you have, the less lightweight you are. They expect it is to support a rapid life cycle. So that is the ability to set it up, and tear it down in microseconds. They expect it to be relatively lightweight in terms of its CPU utilization, its memory utilization, and its I/O. And then lastly, because of all of these previous characteristics, they expect it to be very scalable to the many thousands on any given node. So keep this in, as we're going through the rest of the presentation, keep this in your mind, keep this in mind. Because this is our challenge, is to take DPDK and to take VPP, you know, and these are really applications that were designed to consume all of a core, is consigned to use large amounts of memory and consigned to use large amounts of I/O, and to make assumptions that it's exclusively running on that core, it has exclusive use of the memory and has exclusive use of the I/O, to something that's much more able to share. So now I'm going to jump for a moment and I'm going to introduce FDIO and VPP. So if I show of hands, because I haven't had any questions yet, I'm going to have to make it a little bit interactive. If I show of hands, how many people are already familiar with FDIO VPP? Okay, that's a fair few. Okay. So for a long time in the DPDK community, DPDK was a I/O layer. You know, it was a hardware abstraction layer. It was a way to talk to your network card, to your crypto devices, and also a very highly optimized packet processing environment. We gave you APIs to send and receive packets. We gave you APIs to allocate memory. We gave you APIs to you make most efficient use of the memory channels, to allocate huge pages for your memory, to reduce TLB misses. We had a whole slew of optimizations we built into DPDK. And the idea was that if you built your application on top of DPDK, you would get the benefits of all these optimizations. But what we didn't have was we didn't have an L2 and L3 stack. We had L2 or L3 sample code, but we didn't have a L2 or L3 sample implementation. So Cisco approached us in 2000, at the tail end of 2015, and said, we've had this stack in development internally in Cisco since 2002. It's roughly based on DPDK, give or take today. And we're interested in it, contributing it to the open source community. And in many ways, it was, at that time, what we felt we were missing in DPDK, which was a high-performance L2, L3 implementation. So we built a community around it. We built a community for data plane optimizations called FDIO, with the idea that we could build a series of services around it, and we've contributed. We have a whole bunch of other sub-projects in FDIO, some of which directly use VPP, other of which are kind of related to VPP. A good example of that would be T-Rex, not built on top of VPP, but it's used to test VPP. It's a software packet generator. So we have all these sub-projects in FDIO. So we built a community around VPP, and we call that community FDIO. Well, I don't want to talk too much about FDIO. I want to concentrate on VPP today. So what VPP is a fast and scalable and deterministic L2, L3, and L4 implementation that's being tested. Tested to large scale. It's been tested out to many millions of routes, many millions of concurrent routes, many millions of concurrent flows, to large data throughput. Is also quite deterministic. it uses many of the same optimizations that we pioneered in DPDK. In fact, it uses DPDK for fast I/O. Now, that doesn't mean that it only runs on top of DPDK. It actually uses DPDK as a plugin. So you can turn DPDK off, and you can use VPP without DPDK. And you can use it on top of a Linux raw socket, for instance, an AF packet interface. You can use it on top of NetMap, which is an alternative I/O mechanism to DPDK. You can use it on top of various memory interfaces. It actually supports a whole bunch of different ways of actually getting the packets into VPP. But we like to say that it runs fastest on top of DPDK and uses many of the same software optimizations of DPDK. It's based on vector packet technology, which means that it heavily uses both the SSE and AVX instruction sets. So it typically processes 4 packets at a time. So and that loads 4 packets into the cache while processing 4 packets is generally how it works. Same kind of software optimizations as DPDK. And in the same way as DPDK, it's call mode, eliminates context switching, no blocking, and it processes packets in batches.
Excuse me, Ray?
Yes?
Could we move your mic? When you move it, you can hear the back.
Is that any better?
Could you put it on your shoulder?
Okay, I do apologize.
That's all right. Thank you.
People still hear me? No. A little higher? Okay. Okay. Okay.
Thank you.
Okay. Where was I?
Sorry.
No. That's my fault. Apologies. It's extensible. And it really is extensible. So it has a plugin model where you can add your own plugins into DPK. And one of the key things I just said was that into VPP, DPDK is a plugin. You don't suffer any performance penalty by integrating your feature or your application as a plugin to VPP. We like to say that plugins are equal citizens. There's no performance penalty by implementing your logic as a plugin. It's implemented as a set of directed graph nodes, which means that, and I don't have the deep dive slides here, but you can take it that each graph node is roughly sized to fit into the microprocessor instruction cache. So I might load the DPDK input graph node into my instruction cache, and then I pull in 256 packets off the wire into a single vector. And then I will take that single vector, then I will load the Ethernet input graph node into the instruction cache, and I will push those 256 packets into the Ethernet graph node. That means the cost of loading the graph node into the instruction cache is amortized across 256 packets. You pay once for 256 packets, right? It's got other optimizations it uses as well, but you can take it that the VPP pipeline is decomposed into a hierarchy of graph nodes, and it's a directed graph hierarchy in that packets only flow in a single direction. And it's laid out in a logical way that you'd expect. You go from your I/O, which is DPDK, into L2, which is your Ethernet input, and then into your L3 layer, which is your IPv4 input. And then IPv4 does a lookup and says, hey, is this local traffic or is this remote traffic? It's remote traffic, I send it back out, I figure out where it needs to go, and I send it back out on the wire. If it's local traffic, I'll send it further up the stack, depending. All the graph nodes are configurable by their own. They may have a control plane interface. They may talk something like IKEv2, or they may talk about something like local link layer discovery protocol. There is a number of control plane protocols that are implemented there, but they also have an API and a CLI. It's a very nice CLI, which I'll hopefully get time to show you in a while. And one of the things I love about VPP is its very deep introspection facilities. You never have a moment with VPP where you say, where the hell did my packet go? It's always very obvious in VPP where your packet went. So you can, and that's not these aren't, these aren't debug time features. These aren't features that are only available in the lab to developers. These are features that are actually available in deployed system. The other thing that are also available in deployed system, again, not a developer time feature, is runtime counters and IPC, particularly with instructions per clock. So at any given time, you can log on to VPP and you can figure out where it's really burning cycles, where the bottleneck is in the directed graph. You can also see what errors are being generated. You can see how well it's performing. There's a whole slew of information available at runtime in VPP. I already said it has great packet tracing facilities. And hey, last thing, same as DPDK, it's developed with a standard tool chain. Nothing funky about it. It uses auto tools, make, GDB, GCC. Nothing unexpected. So, I actually have a recent kind of releases slide next, but you can take it as a fully featured layer 2, layer 3, and now layer 4 implementation. And we're going to talk about the layer 4 implementation a little bit more in depth in a while. But at layer 2, you get the kind of things you expect, like MPLS, VLANs, Q&Q, those kind of things. At layer 3, you again get the things you'd expect, like IPv4, IPv6, overlay protocols that typically go along with it. One of the things that might be interesting to take us as wireless talk is we recently added GTPU as a feature to VPP. So you have, if you're looking to encapsulate over a GTPU, you can now do that in VPP. But hey, there's a whole bunch of actual overlay protocols. One of the big things that we did at Intel this year was we accelerated the IPsec implementation in VPP. So prior to the work that we did in the IPsec implementation in VPP, it was roughly getting about 1 million packets per second through the IPsec implementation because it was based on libcrypto. What we did was we re-engineered the VPP IPsec implementation to use the DPDK CryptoDev implementation. What DPDK CryptoDev does is it takes advantage of the whole platform crypto performance. It provides access to both QAT, which is available in the Lewisburg chipset. QAT is our crypto acceleration unit. Or you can use Encore crypto acceleration, which is the AESNI instruction set. And what we were able to do was we were able to optimize it to the point where with just three cores on the Perley platform, we were getting 100 gigs of IPsec through VPP using the QAT acceleration facility in Lewisburg. Without the QAT acceleration facility in Lewisburg, we were able to get 100 gigs through with 8 cores using the AESNI instruction set on core. In L3, you obviously get things like discovery and get segment routing as well, which is another overlay technology from Cisco. And then in layer 4, UDP has been there for a while, right? So you need UDP for things like VXLAN overlays. Well, then more recently, a TCP implementation has been added, and it's a much talked about TCP implementation. It's made a lot of interest in it at the moment. And the TCP implementation is, we'll kind of go into it more depth in a while, but it really is a grounds-up TCP implementation. Oftentimes when you see TCP implementations, it's a reuse of the Linux kernel TCP implementation. I don't know if people are familiar with the Linux kernel as a library project, which is a TCP implementation user space. Another example that uses the Linux kernel in user space as a TCP implementation. Another example would be FStack from Tennyson, which is a user space TCP implementation based on FreeBSD, and there's quite a few user space TCP implementations based on FreeBSD. This one's different in that it's written from the grounds up TCP implementation in VPP, which means the TCP implementation itself is not scalar. It's not a packet at a time that like what you'd usually see in the kernel. It's a vector TCP implementation, which means that you aggregate all your TCP connections in VPP, and then it processes, TCP packets in batches, and then splits them out into connections, and then batch processes connections, and it's very, very efficient TCP implementation. You get quite a mature control plane, so you've obviously got an API, and you've got language bindings for the API to Python, Perl, Java, the kind of languages that you'd expect. It's also got a very pretty cool CLI, and you'll see that in a while. It's also got IKEv2. One of the things that was recently added in a few, I can't remember if it's the release that's just gone or it's the next release, but we're adding a BGP implementation in VPP so that instead of, before people were reliant on the BGP implementation that came with ODL, now actually there's a BGP implementation actually in VPP itself, so you don't need to rely on ODL to do your route configurations. Usability, it's got language bindings, as I said. It's got plugins for OpenStack and ODL. It's got a plugin directly for the OpenStack Neutron ML2 plugin called Networking VPP, and it's also got support for ODL for group policy-based routing. It's also got support in Kubernetes and Flannel. Sorry, not Flannel. I think that's actually incorrect. It's actually Contiv now. So a lot of work has been done stitching VPP into Contiv and Contiv as a CNI provider into Kubernetes. And now we're drifting into the control plane stuff where I feel very, very unsure. So I'm going to move on. And then finally, we've got OSV packaging, which means that hey, if you're using Ubuntu or Debian, we've got you covered. If you're using CentOS or Fedora, we have packaging for you as well. So then, look, I'm not going to talk through this slide in depth, except to say that the VPP as a community is being rapidly evolving. You can see there's a whole slew of features that have been added in 2017. One thing that I like to talk about here, I like to talk about two things here. One thing that I like to talk about is obviously that we're adding a mass of features over time. The other thing is that we're doing a lot of work, performance testing, to make sure that as we add features, we're not actually degrading performance as we go. And this is a key thing, and it's a key tenet of FDIO and VPP, in that we have a sub-project called CSIT where we're constantly measuring. We run performance tests on VPP for a large set of test cases to make sure that as commits get added to VPP, there's no degradation in performance. So as it becomes more featureful, as may be the case that's experienced perhaps with other projects, as typically happens is as a project becomes more featureful, you usually pay a cost in performance. We're pretty determined that won't happen in VPP, and we have a whole series of test cases in a sub-project called CSIT that are tested continuously to make sure that as we get more featureful, we're not dropping performance. One of the common themes, you can see a couple of common themes in, let's say, 2017. One was IPsec, which I just talked about a few moments ago. Another one has been the TCP implementation. There's a lot of work. The initial version of the TCP host stack was made available in 1704. And then it got a lot of RFC compliance testing was completed between 1704 and 1707. So it became a much more RFC compliant TCP implementation over that period. Something again that was added in 1707 was a series of interfaces to support containers. So to support VNFs and containers. One was MEMIF and the other one was Virtual User. And then there's been a whole bunch of networking features added since then. Another thing we added was GRE over IPv6, which was another overlay. That was something that we added. But look, I'm not going to read through this at length. I just really wanted to leave the two impressions. We're adding features, list is growing with every successive release, but also performance is not being compromised as we add more features. Okay.
Quick question on the TCP stuff. You mentioned there are multiple, if there are multiple TCP sessions, connections, then you can batch it, etc. You will definitely get a much more better performance.
Yep.
A single TCP connection, the Linux kernel stack has tons of pretty interesting TCP modification. Like initial window can be higher, window scaling, adaptive stuff, there's so many things actually. But given this stack, probably will be very much, as I looked at it, it says fast recovery and basic TCP state machine, right? So probably it doesn't apply for the single connection case, that's my understanding. Or if you add those kind of features which Linux already has, then maybe it might be comparable. That's what is my observation.
So when you aggregate all of the TCP processing in the vSwitch, you can make a lot of the economies of scale that we talked about, the kind of optimizations that we talked about, the TCP implementation gets the benefit of. So if we think about what the kernel does, the kernel, and by the way, I've worked in and out of the Linux kernel for years, and but I'm a huge fan of the Linux kernel. What it does, like one of the things that it implements is GRO. So that's the ability to assemble the TCP stream in the networking driver before it pushes it up the stack. Why does it do that?
The segmentation offload you're talking about.
It does that to assemble basically a jumbo frame. And so you're not paying the per packet cost. The per packet cost as you move the packet up the stack. Whereas what we do is we flip the stack on its head. So it's not those kind of costs that are typically associated with GRO turned off, where you're paying for a function call for every action you do on the packet. So GRO's way of solving that is to aggregate all the packets together and to process them all at once. Well, we do 256 packets at a time, typically in VPP. So it's similar in that respect. But then we also get the benefit in the TCP implementation of things like the vector instructions, things that the kernel typically doesn't use. So the TCP implementation that we end up with, actually implemented in VPP, uses microprocessor optimizations that typically aren't used in the kernel. And also it gets the benefit of those kind of optimizations we talked about before, like the amortizing the single instruction cache load across 256 packets. The kernel does part of that by GRO, but I'd argue that we actually end up with a more efficient.
Yeah. Another thing is a branch prediction, the if likely, unlikely kind of instructions in the kernel. Just before, one last question.
Well, there's another way of approaching that, and that's again the way the TCP. So when you say likely or unlikely, what you're doing is you're giving hints to the branch. You're giving hints to the branch prediction unit. Whereas one of the fun things, one of the interesting things that VPP does is it assumes that all of the packets are going to the next default graph node. It assumes that all packets are going to the next default graph node. And then it goes back and it handles exceptions on a case-by-case basis and then changes them. And it actually turns out that's actually far more efficient to do, to make assumptions that, hey, I've got 256 vectors. And a good example would be, let's say, IPv4 lookup. You make the assumption that they're all going to get looked up and going to go out on the wire. But then you go back and you identify the ones that are actually local packets, because out of the 256 packets, they'll probably be just onesie twosies out of 256 packets, and you identify those on a one-by-one, and you handle those on a one-by-one basis, and that's far more efficient way to use the branch prediction unit.
Yeah, one last question on that. Your last slide mentioned about tracing mechanisms. So, yes. What kind of tracing mechanisms with zero are you using?
I'll show you in a while. Okay. I hope, if I get as far as the demo. Did I have a question here? Yeah.
Yeah, I'd like to know the driving factor behind putting TCP into the fast path, like assembling the TCP and all that. Is it something like for firewall processing? Or? Okay,
it's actually very much targeted at containers kind of use case, and I'll come on to describe that in more depth in a moment.
Hi, 2 questions.
Sure.
You mentioned BGP. It's a data plane processing. All you need to do is to look into its me destination 179, potentially if source is configured and punted to the application. What do you do specially for BGP?
I'm sorry, I didn't quite catch the question.
You mentioned BGP specifically.
Yes.
It made sense when it was an ODL at the management layer.
Yes.
What are you doing now specifically?
So that I don't actually have the detail of. So all I know at this point is that their BGP implementation was previously handled by ODL. Now, I know one thing that we're trying to do is decouple VPP. So one of the things, for instance, we can have the networking VPP plugin. So you have an ML2 plugin directly from OpenStack down to VPP with no dependency on ODL. And then for those people who are using the ML2 plugin, not using ODL, I think the BGP implementation was made available in VPP for those set of users who weren't using ODL. But that's as much as I know about it.
Second question, gRPC, so streaming telemetry. I remember
If you do send me an email about it, I can find out more information.
gRPC. Intel last year announced that gRPC is going to be implemented very low layer, somewhere within SPDK. And are you going to use gRPC for telemetry streaming?
I don't, gRPC, general.
Google RPC?
Hmm?
Google RPC?
Oh, the Google RPC. Oh, that's a good question. So no, I don't know where, okay, so there's Golang bindings for both, I know of a project that's doing Golang bindings for both DPDK and another project that's doing, there's a new sub-project in FDIO. I know neither of these are gRPC, right? For FDIO. But I don't know anybody who's doing gRPC for either of them. So this is basically like what VPP has is VPP has pretty much a binary socket implementation. So it has a way to talk to it over either TCP sockets or Unix sockets. But it's not quite an RPC. I wouldn't quite call them RPC implementations.
It uses netconf push nurse boundary,
Okay,
which is very inefficient.
Well, okay, to be precise, what it does is you talk netconf and yang to honeycomb, which is, and then honeycomb talks to binary API to VPP. But I'm not aware, I know there's Python language bindings, and I know there's Java language bindings. I'm not aware of any gRPC implementation. Okay, so how am I doing for time?
You are at your 15 minutes.
Oh, okay, gosh. All right. So you end up with two problems. One is how do you talk from a VPP-based vSwitch to containers? And how do I run VPP and DPDK inside containers? How do I talk from a DPDK or VPP-based vSwitch to containers? You must remember, VPP and DPDK are user space and containers are really an entity at the kernel. And then also, how do I run DPDK and VPP efficiently inside containers? So those are the two use cases I'm going to talk about. So the first use case is, how do I efficiently run DPDK and VPP in the kernel? So how do we efficiently run DPDK and VPP in containers? So you might remember the matrix, the list of characteristics of containers and microservices I presented earlier. Well, I like the picture of the round peg in the square hole because I think that kind of roughly describes where our starting point was. You know, we weren't container friendly starting out. And whereas I think, you know, the kind of microservices, how do we get to a strict microservices model is still some way off. I think there's a lot we can do today and a lot we are doing today to make ourselves more container friendly. One of the things that we're doing is that we're optimizing the startup. So we're getting DPDK to start up faster. You can do things like if you know you're running inside a container, there's no need to scan the PCI bus. There's no need to look for contiguous memory if you're using a pure virtual memory interface. You can do things like you can use 4K pages instead of using huge pages, and you can use late binding of huge pages. You can also, we already support interrupts in order to do better core sharing. So we also have an interrupt-driven model in DPDK instead of a poll mode model in order to share the cores in a more efficient way. And then we also have enabled multiple I/O methodologies for containers. So you can support SRIO via pass-through, that's taking a virtual function, passing it through to a container, and then running DPDK on top. But we also have a virtIO user, which is a pure memory interface from your virtual switch into the container with DPDK sitting on top. Similar story in VPP, which is that it actually starts up relatively quickly if you're not using DPDK as a plugin, if you're running on top of the raw socket. Obviously, we want to improve the situation where you are using DPDK as a plugin. You can use the VPP's own memory model, which already supports 4K pages and late binding. And then VPP, same as DPDK, already supports interrupt mode instead of poll mode, SRIOV in containers, and in addition to supporting virtIO user, I should say, it also supports its own memory interface into the container called memif. So all of these are activities that are in flight at the moment that you'll see in DPDK. Oh, this is a good one. I think we're 1708 is live, so I think it's 1711 is where you'll see a lot of this will see the light of day. pretty much but the two key takeaways that you can take away are that we are making the key takeaways that you can take away is we're making DPDK and VPP more efficient in terms of how it shares cores. We're making it more efficient in terms of how it shares memory. And then we're also making it start up and shut down faster for more friendlier container deployments. Okay, so that covers deploying a DPDK or VPP inside a container. What if you're a DPDK or VPP based vSwitch? Or this is where you use DPDK or VPP in your NFVI and you want to talk to containers. Because many of us, many deployments already use DPDK and VPP as their vSwitch for talking to their VMs. Now we want a situation whereby we're using that same technology to talk to containers. So this is where the TCP implementation becomes interesting. So VPP already supports MEMIF for VNFs. So if I have a VNF in a container, I can talk to my virtual switch over the VNF interface. So that's a pure in-memory interface where I share a memory I/O area between the virtual switch and the VNF, and then I punt my packets over it between my VNF and my virtual switch. And you can do that already today with both DPDK and VPP using either VirtIO user interface or using MEMIF. It's already well supported. So this is really where you have a VNF. The VNF expects a raw packet interface, not too dissimilar to VPP, it's not too similar to DPDK. That's already well supported for those kind of container deployments. But that's where you see all of the kind of characteristics we talked about before coming into play for the VNF and the container, ability to start up and shut down faster, etc. From the vSwitch's point of view, the vSwitch sees a MEMIF interface or a VirtIO interface, not too dissimilar to the VirtIO interface that it's been using already for VMs. Where it gets different is when you want to start talking to socket applications using this methodology. And this is, remember, this is all bare metal deployments now. This is containers talking to a vSwitch in the default namespace. So you might have a socket-based application in a container. Now, the model that's been supported up until this point has required that you hairpin the package through the kernel in order to get up into the virtual switch. And it's very commonly done at the moment, which is that if I have a socket-based application, that socket-based application expects to talk to the kernel. The bit stream, the TCP bit stream flows from the socket-based application in the container into the kernel, then goes into a vETH, and then from the vETH front end in the container into the vETH back end in the default namespace, and then hairpins back up into the vSwitch. So I think you probably can count 2 or 3 context switches along the way there, 2 or 3 memory copies along the way there. Doesn't really sound terribly efficient. So what the work has been happening in the VPP community has been to develop what's called the LD preload layer, which will intercept the socket, the TCP bit stream, as it leaves the socket application. So the socket application doesn't really know anything has changed. The socket application still thinks it's talking to the kernel. But that bit stream, that TCP bit stream, has been intercepted by the LD preload layer and now is redirected over a shared memory interface, not too dissimilar to MEMIF, into a TCP implementation in the vSwitch. So this is where the scaling really starts to happen. So you no longer have a real interface. It's a lightweight in-memory interface compared to a vETH. The socket-based application doesn't know that anything has changed. The socket-based application still thinks it's talking to the kernel, but now it's talking to the aggregated TCP implementation in VPP, and that aggregated TCP implementation is designed to scale to many thousands of containers because you don't have a real kernel interface, because it is a relatively lightweight interface in the kernel, and because you're implementing a vector TCP implementation in your vSwitch, you're ending up with a far more scalable TCP implementation that should support many more thousands of containers. So this is one model. This is a model whereby I want to use, this is one model, there's a lot to like about it. And this is where I want to support a bare metal deployment. And where I have a memory interface between my virtual network function and VPP, And then I use the LD preload layer between the container and VPP. Now the LD preload layer is in development at the moment. You can imagine that out of the box it will support Nginx, Node.js, Redis, but it won't support every socket-based application that exists. So we also need a transitory approach, a way to transition for those set of applications, that may not be supported by the LD preload layer over time. And because of that, we're supporting another model, which is called the master VM approach. And in this approach, you deploy all of your containers in a single VM, the master VM. And the benefit that this gives you is that you can continue to use the Linux kernel in the way that you've used before, that you used it for virtualization. You get the benefits of VTX in that VTX deprivileges the Linux kernel, and by deprivileging the Linux kernel, deprivileges the container as well. So your socket-based application running inside the kernel, your socket-based application running inside the container talks to the kernel. The kernel is now running in user space. It's running up in ring 3 by virtue of VTX, by virtue of virtualization technology. And then it talks to the virtual switch over a plain old VirtIO net connection that we've been using in virtualization for years at this point, 7 or 8 years at this point. This is already a very well supported model. We have VirtIO net drivers in DPDK for the last 5 or 6 years. And VirtIO net has been supported by the Linux kernel for the last 5 or 6 years. What we're doing here is we're using the benefit of virtualization technology, VTX, to deprivilege the kernel, and by deprivilege the container, and by moving the container up into user space, we can use the standard virtualization toolchain to talk to the container. So I can talk to it over VirtIO net, an interface that's already well supported by all virtual switches. I can use vhost in order to set up the shared memory blob between either the virtual switch and DPDK running inside a container, or between the virtual switch and the kernel, the kernel's interface inside the container. So what this does is has a leveling effect. I can now talk to my container in the same way I talk to my VM. I don't need to make any special adjustments. And in this way, this is why I talked about it being a good transitory approach along the way to containerization and microservices. Because for many people will be in a situation whereby they'll want to run all of this concurrently. There won't be a big bang in their network where they'll turn off their virtual machines one day and turn on all of their containers another day. That's just not going to happen, right? We can expect that virtual machines will have a long tail into the future. They're going to be around a long time. So we are going to need NFVI that will support both virtual machines and containers concurrently. What this does, or what this approach, the master VM approach does, is it makes it transparent. Your containers look like your virtual machines as far as the vSwitch is concerned, and your containers look like your virtual machines as far as your NFVI, as far as a lot of your NFVI is concerned. So it has this leveling effect. So I might have a DPDK deployed inside a virtual machine, and I can talk to a DPDK-based vSwitch over VirtIO net connection. Or I might have a socket application deployed inside a virtual machine. I could talk to my DPDK-based vSwitch over a VirtIO net connection. Or I might have a DPDK VNF or a socket-based application talk to a container deployed in a container within the virtual machine. And it talks over the exact same VirtIO net connection. Now, some people, when they've seen the slide, they come to me and they say, well, you know, Ray, you don't get the point. Virtualization is containerization is the rejection of virtualization. I say, well, I don't want everybody to run lots of virtual machines. I just want you to run one virtual machine and put all your containers in it. Because that lets us use VTX to deprivilege the virtual machine, and then I can use the same virtualization toolchain to talk to all those containers. I still get the economies of scale, and I still get the efficiency of containers, but then I also get the benefit of VTX to deprivilege the containers, and I've got a much nicer way to talk to them from my NFVI. Okay, so how am I doing for time? Okay, I've got a question here.
So you had mentioned about the LD preload.
Sure.
So So I can understand that it is essentially going to handhold the packet from the container space onto the vSwitch.
Yep.
So, but can you throw some light on what context this is going to run? Is it just going to be as simple as a function call or an API?
So the application itself, so if you think about how an application, a Linux application typically runs, you run your application and it calls the runtime linker. And the runtime linker says, I need to load glibc and I need to load these other libraries. So what they use is they use a facility in the runtime linker called LD preload that loads a given library before everything else. So that POSIX API call that we're all familiar with, the listen, the connect, the send, the receive, and then the read and write, and all of those other semantics, all of those API semantics you expect with a TCP implementation, they no longer are calls to glibc. The application still thinks they're calls to glibc. It doesn't know anything's changed. But now they're actually called to this intercept library. So the intercept library, now is responsible handling the TCP connection. So an example might be the intercept library might get a listen call, and then it sets a flag inside the VPP vSwitch to say, hey, if you see any packets that arrive at this IP address and this port, send them to me. Send them over this shared memory area to me. Similarly, when packets are sent and received, when the VPP has a session implementation, has a notion of a TCP session, it's going through the TCP sessions. It will see that socket, it'll see that port number, and it'll see that IP address and say, okay, that's belonging to this bit stream. I'm going to push it in. I'm going to put it into this. I'm going to put it into the TCP window for that bit stream, and then I'm going to wake up that socket-based application in the container way to process the bit stream. So all of the API calls that you'd expect to go to the kernel are now faked out by VPP. The socket doesn't know anything has changed. It still makes a select on the socket to be woken up whenever the TCP bit stream has become active. It still does a listen for new connections. It still does all of the things that it's done before. It shouldn't know anything has changed. But what it does end up in the case is you are aggregating all your TCP processing in the vSwitching and getting those economies of scale. And then you're also removing the VEATs from the equation. So you're ending up with a much lighter interface into the application. But theoretically, the application wants to scale. Now, anybody who's done any socket-based programming will be able to tell you that the different permutations of different options you can select on sockets, there's a very, very, very large number of permutations. It's actually all different permutations that I can do forks, and what happens to my file descriptor when I fork. There's also what happens, there's a million different ways to use the TCP API. So that's why my expectation is that we're going to need both approaches for a while. So my expectation is that there'll be a couple of high priority applications that we all know and love in this room, like the Nginx's of this world, and they'll be made to work great against this LD preload layer. But for all those many different permutations of TCP applications, we also have the second approach, which is to use the existing kernel stack and to make containers more friendly to the NFVI by using virtualization to deprivilege. And I think it'll be a mix of both. It will come to a mix of both. Well, it may be the case, and I hope it will be the case, that we'll scale the first approach to support all socket-based applications over time. But we're going to need multiple tools in our toolbox in order to support a scalable container data plan. Sorry, I have a question.
So, thing is about select and epoll is more tricky. Because
I'm sorry?
Select and epoll, for example. Application.
Selecting
and epoll.
Yeah,
two system calls.
They're the two trickiest ones.
Because the application can open, let's say, FD for a Unix domain socket.
And they're the hardest ones to get to scale. So what's actually interesting that's happening is not only is there the LD preload layer is being made available, but a native TCP implementation, a native library to talk to the VPP TCP implementation is also in development. Because as you quite rightly pointed out, that the two hardest API calls to get to scale are epoll and select, probably the two most inefficient. So if you are willing to put the investment in to rewrite your application to talk directly to VPP, there is a second library that doesn't use it doesn't use ePOL or doesn't use select, but pretty much implements all of the other BSD SOCKS API calls. By the way, that's a common theme you see in all the TCP implementations, is they all end up with ePOL and select as a bottleneck. So the second library is not transparently loaded by application. You have to consciously link against it and use its API, but you end up even more scalable again by virtue of not having to fake out ePOL and select. So that was a great question.
I have a question.
You mentioned you can connect VP with the containers with either MEMIF or the
Yes.
socket over what's that, LD preload.
Yes.
Are those interfaces still wrapped by standard network stacks, or you can pass some private data along with your package over those kind of?
So those are very much raw interfaces. They're kind of like.
Can you repeat the question?
Oh, sorry. Good. Oh, right. So do the apologies. So the MEMIF and VirtIO, the MEMIF and VirtIO user interfaces, do they pass to the entire network stack? They do. So when you receive packets via the VirtIO net connection, it depends on which network stack you mean. If you mean the VPP network stack,
right,
the answer is yes. Do they pump packets into the kernel? No, not unless you do something extra. But yeah, as far as VPP is concerned, I remember at the head of the presentation I said VPP supports lots of I/O methodologies. This is another I/O methodology that VPP supports.
But can you pass private data along with the packet over those kind of interfaces?
It actually came up. That came up recently in the mailing list. Was that you in the mailing? Because that question came up in the mailing list recently, and the answer I can't remember off the top of my head. If you send me an email, I can chase it.
Okay, one more question.
Yeah. Pretty much you are doing what the kernel has been doing for quite some time. One of the reasons why we have this isolation or the separation between the kernel and the user space is that user space would not be able to corrupt the kernel. Now if you're pushing all this processing into the user space, anybody can step onto anybody else, especially if you have shared memory. Even multiple containers can step on each other. And how are you going to address that? And it also adds to the security issue.
So that's a great question, and I've heard that a number of times. And I can dial us back to, all the way back to the operating system designs in the 70s. So you ended up with the executive, and the executive took care of device management. Took care of things like managing the time in the CPU, managing I/O, and managing memory. But it was a very different model. In that model, the networking wasn't the application. When we're implementing a VNF, for instance, networking is the application. So it makes sense in that case to have a user space. Like when the networking is the application, it makes sense to always run the application user space. So that, hey, I'm protected by an IOMMU. So if I have an errant DMA, I don't bring down the whole system. I only bring down my application, because it's in user space. Hey, I can spin it up again. Whereas, so my argument very much is once the networking becomes the application, as it is in DPDK, as it is in VPP, it's the same with any other application that runs on top of the system. It makes sense to run in the user space.
VPP and DPDK, they are stateless. For example, one packet has got nothing to do with other packet. Whereas if you bring down the sockets, that brings down the application itself, pretty much.
That's true, but you can make the argument there is no more or less failure resilient or resistant than the kernel, because if you're aggregating all of the TCP processing in the kernel, the only delta is at that point if you have an error and you bring down the entire system. Whereas if you have an error in DPDK or VPP, you only bring down the virtual switch, and you still have the opportunity to spin it back up again. Okay, I'm done. I'm yanked off. Do I honestly have no time for a demo? Okay, it doesn't.
Dr. Sujata.
I need 2 minutes.
Yeah.
Okay. Okay, it's not going to work now because of course it won't. Okay, oh, it's live. Okay, but you can't see it. Why can't you see it? Okay. Oh, what happened? I don't know.
You need some help out there. You knock on the window.
Just shrunk the window.
Oh, no. Okay, that's it.
Hang on, he's getting some help here.
Oh, okay. Okay.
Oh, yeah.
So, Okay, I can make this really easy, which is I'm going to just drag and drop this notepad window across here. So I'm going to do something really simple. I'm going to create a couple of, I have a couple of containers that are spun up. One's called container 1, one's called container 2. They have a V8 backend, which is called V8C1, and it has V8 backend, which is called V8C2. I'm going to put them up out of the default namespace. I'm going to pass them into VPP as a vSwitch. And how I do that is I tell VPP they exist. I say create host interface name V8C1 and C2, and that creates interfaces in VPP for the V8s that talk to C1 and C2. I'm going to set their state to up because I want to talk to them, and then I'm going to set them into a bridge. I'm going to add them into an L2 bridge. So this is nothing terribly fancy, and then I'm going to show you that they're added into the L2 bridge. And then because I'm doing all this with my neck kind of crank, I'm going to just copy and paste it. That's okay. Okay. So sudo VPP control, so this gives me access to the VPP CLI. A lot of the facilities that we talked about there's runtime statistics, there's errors, things like that. Okay, so now I'm going to show you the interfaces beforehand, show int. Okay, I've only got the localhost interface, the loopback interface. So I'm going to pick up my, okay, where's my, okay, it's over here. So, okay, so now what I've done is I've created my, my virtual interface, two virtual interfaces in VPP, one to talk to C1, one to talk to C2. I've added them, I've set them up, and then I've added them to my L2 bridge. And I'm going to show you my L2 bridge now. Okay, there's my two interfaces, and they're both added to VPP's L2 bridge. So now I'm going to do something. I'm going to jump into container 1. C1. So now we're in C1. Okay. Where's notepad gone? Oh, there it is. So now I'm just going to add an IP address in C1, so you can see me just add an IP address to the V8 in C1. Okay, I've added an IP address to the V8 in C1. And then, predictably, I'm going to add an IP address to the V8 in C2. Where's my mouse pointer? Oh, it's over here. Whoops. Yeah. I've just made a huge mistake. So of course, this is usually why demos blow up, but we'll try. Okay. So now I'm going to flip over to C2, SSH C2. And I'm going to add the IP. Okay, so now I'm going to ping 172.16.13.12. And there we're pinging. And you say, okay, well, that's not miraculous, right? You likely are pinging not through the virtual switch, but through the Linux kernel. So like any good magician, I'm going to show you that I am actually pinging through the virtual switch. So I'm going to add a tracer to the graph node, the AF packet graph node, which picks the packets out of the Linux kernel and pulls them into VPP. So I say, okay, trace, add AF packets. So I add a tracer to the AF packet graph node, which pulls the packets out of the Linux kernel and pushes them through VPP. So I add a trace, and then show trace. And there we go. So by way of an example, there's packet 6 that got pulled in. It arrived on the AF packet graph node. It then went into the Ethernet input graph node, who said, is this packet for me or is this for somebody else? This packet's for somebody else, and then it pushed it into the bridge. And then in the bridge, it decided where it needed to go, and then it sent it out on the host v8c2 output. So it sent it out to the right container. Oh, sorry. Incidentally, that was the reply. That was the reply, not the echo request. So that was it. As simple as could be. I had two containers, C1, C2. I had VPP acting as a vSwitch between the containers. I redirected the V8's backends of the containers out of the kernel and into a VPP vSwitch, and then I pinged the packets through the vSwitch with just a handful of commands. Simple as can be. Okay. I think I'm well out of time at this point. I am well out of time. Thank you so much.
Don't leave yet. Sit down. Renee and I'll be at the doors to hand these out if you want to talk about it.
Okay. Do you need me? No? Okay.
He's sticking around, right? People can.
Oh, yeah. But when you said that don't leave yet, I didn't know whether you were me or everybody else.
We want you to stay around too.
Okay.
Yeah, so people on the stream will be back after dinner, like at 7:20 maybe?
Yeah, we had planned to come back at 7:15, but we've run over a bit.
Yeah, so 7:20 probably.
Yeah.
So on your way out, Renee and Michelle have idea relay cards. So the way it works is you have 3 cards, and one has network component, open source project, and type of project. So you pick the cards. It's like, your luck, what component you'll get or what kind of project you get. It's a permutation and combination. So you get 3 components, and you choose. You don't choose, you get something, and then you pitch a project on that. So that's idea relay. So grab it. Yeah, you can work in team also. So you don't have to do it individually if you want to do 2 at a team or 3 at a team. Okay. So on your way out, grab those cards, and is dinner served?
Dinner's out there, yes.
Yeah, I heard that dinner was a little late, but yeah, it's served now. Okay.
We've run into each other. I was just telling you, I knew nothing about networks, and I learned an enormous amount from that. Oh, yeah. Yeah. Yeah.
Oh, he did say yes.
So the one thing I think I have to change, first of all, our intercept mechanism, the preload, the LD preload, that's it. So I do we be able to.
What about the MEMI?
Yeah. No, that's good. That's what essentially what I'm using in the West channel. It's not the MIS. The one thing I have to change, so I need to set in touch with comments. Instead of getting a packet set up, okay, so I just need to do this place for you to so that I would it's like a research mission, so you can it's like a week or 2 days or I don't want to work in it looks like essentially you're able to
I was thinking we could do
Yeah, no, but for two, yeah. Well, we have to redo it because there's a lookup version. But, you know, it's open source. Yeah. But the idea is
Тупо потому что другого нет. In Jamaica, I used to work.
Yeah, I don't have to. I understand that. There was an issue with yeah, especially if you can.
Well, we have a lot of work to do with
I have to see how to
So I think, like, if I have a situation where I say yeah, sure. What you want is
well, they're not actually
So at the end of the day, when you get
Is this something Mr. Carlson did a great job?
I was involved.
We're actually just like
Yeah, run the competition, right? When you talk about
This is something that's
those type of
so that's something really and that's also more
come back or whatever.
and you know, this is something that's very common.
It's just one marketing server, so it's not because anyway, oh, it's recorded. So I hope that you think that you ping an email and you want to link to the whole thing is recorded. Yeah, and also when if they need a new one,
Oh, the Indian ladies, yeah.
So Sujata has the actual specific information. But if you give me an email, I'll introduce Oh yeah, absolutely. Yeah, I say both the email and first recording and the deck. But it's all public. It's all big. Orange Telecom. Shouldn't you get some friends?
Now, if you pipeline, collaborate in a very like standard. Okay. So
because today, unless you last year,
exactly.
So you pay in the something like that.
and it's further we have a collaboration using the Nokia base station to demonstrate each of these done by broadcasting
You just came at the right time. We didn't miss the most important presentation because my colleagues were going to show me video streaming over the wireless network. So I talked about virtual switches, containers, GPDK, but the actual wireless presentation is next. So you didn't miss that at all. And it's my colleague Christian. You look at that. Daniel Moore's talk on it. I was just warming up your presence. I am. Yeah, we know what you're doing. You work with Monica, right? No.
And it's needed for you to
Oh, you were for oh, yeah. On virtualization? Or?
So at the end of the day, kind of support the way you usually chip for the next week.
Oh, that's right. Yeah, we were called to get a research with Eric. Yeah. Okay, it's good to meet you. Did you catch my presentation? We got some food?
Except for half.
No, after you, sir. Hey, are you coming to Dublin? Dublin? Yes. Swedish place.
I am not. If you don't come to Dublin, I'll never forgive you.
So I hope I didn't walk on stage too. I presented at the NFV conference in Beijing in
difficult.
June, and I had 3 hours. And I went up to say, I just wandered around the stage randomly. And then I said, hang on, these guys don't only have to track me, but they also have to translate from English and stuff into so yeah, I wasn't so sorry for walking around, it's my bad. Some people can just come in a whole stand like this and then do that.
Yes.
Do that like
Summertime, right? I had to. This is the general area you should look, and then transition back to showing.
Okay, let's go.
have you tried copying and pasting on a giant screen? No, it's great fun. You should try.
What do you do? Well, it's just like there's the video track, and then they're just adding another track. So either
Did you
kind of the side photo, like basically making the front of the screen. So it's like you're sitting there and you see
Oh, okay.
Yeah, we can
Yeah, you don't say confidential, right?
No, we can't.
We wouldn't do it.
You do?
Yeah, we can look up. Yeah, we have the deal.
Oh, so we have separate calls.
Yeah, yeah. Okay, thank you.
Because then you see like, okay, you can see the block has so they absolutely are supported.
No.
Like I said, you slide this, there's two large. One reload is require you to make any changes to the application. You know the one you sent me in that case, right?
Oh, okay.
More than half of them. I can't have the
So that's just sometimes I don't like the response. Yeah, that I don't like it. So I just that is clear. Because like the one you said, it's what's
You could, if you need to test,
that is good. It didn't use the response. So you need to put a hyperlink that doesn't translate. So for at least looking for both, join us. Okay, so make sure you guys get the scale. No problem. Because the next to the start, yeah, it's nice to go fast.
I don't know too much in the detail on it, so it's actually worth us having a conversation with anyone. Yeah, sure. Actually, how do you? I can't tell you that the bottom line is a nice scale, and that's what caused the. That's what's caused the work.
yours is simpler. Intel always.
I'm waiting in line, and I do need to leave in 20 minutes because I have to catch a flight. I have to catch a flight. Well, listen, if you're interested, have a call. If you're interested, have a call. If you have an NDA with each other, you can have a call and we run the content for you. What you can do, you can do the same thing. Look at the press, video of the press, and then have a call.
Yes.
Okay. Well, what I can do is, do you have a laptop? Okay, send me what's your email.
So you just what?
Yeah, you just saw me there? So you are.
I don't know where the
It's good enough. You can come to this room.
No, that's bad one.
So when you come to this auditorium, just about that come to that lobby.
24 hours. This one, this is the rendering.
Probably dropped off on Friday. I had a meeting most of the day. That way she can have a battery. I don't want it. She tried to give me stocks these things. No, that's okay. I give things away because I get too many of them. And the battery and giving it as a choice, you know. It's a small one and fit next to the phone. And
6 hours.
you know, people get up there.
Oh, different.
I don't know how much.
Just let me do this.
You showed your
Because they might bring back.
Yeah.
So question.
idea about the video.
Yes. That was I didn't want to make people even more confused by talking about their containers, but you're absolutely right. So what you can do is, if we flip back to this slide, so it really depends on what you want to do. So you may have applications that you want to that they are the same. You may have applications
switches that you want to run via. And then you want to run a clear container. What this model does is it actually means you can run more concurrently. So you can what really should happen is you should have clear containers. So you could have a virtual machine, it's just a DNF, you can have a virtual machine, or you can have master DNF with a large number of containers, or you may have a clear container where you have virtual machines. And what this does by using this approach is that you can support them all with the same enterprise virtuals. Yeah, you may be this kind of containers to discuss the approach. Because remember, it's all just there to know needs, right? Or you may be in a situation whereby actually on this particular node, that isolation between tenants doesn't I just want isolation between tenants and the host, and then I put them all into a single VM, and then I have the isolation between the tenants and the host. Or you may be in a situation where you say, okay, well I don't have the packaging for this yet, so you put a virtual machine on the side. And what this methodology does is it provides a way to support them all. Does that make sense? Oh, sorry. That's okay. Oh, well, no comment. Okay, lovely to meet you. Yes, no, I'm actually, Phoenix. Yeah, I'm Phoenix, but I'm actually based in Ireland. Yeah, Phoenix was so. Oh, great. Yeah, Ireland? Yeah. Oh. So my home office is Ireland, but I mean, some Phoenix for some, like my boss is based in Phoenix. Oh, that's why you wanted to visit. He wanted me to visit. He told me the weather would be beautiful. The Phoenix is very hot, over 100 degrees. Just a bit. And I'm from Ireland. I like it's cold. Yeah. Ireland cold? Yeah, it's like 46 degrees in Phoenix at the moment. I think the temperature in Ireland is 16 degrees. 16 degrees. Okay. So I'm plus 30 degrees with me. Oh, okay. I'm Reagan's. Yeah. Absolutely. Who's your phone? Oh, really? Yeah. Wow, real car? Oh, really? You're based in Taiwan? Oh, I'm from Taiwan too. Oh, really? Yeah. Nice to meet you. Yeah. So I have a long history of doing work at Ericsson. I did the original host implementation of DPDK, and that was for Ericsson. Not really. I'm just a software solution architect for IT. Okay. Yeah. Okay. We are more focused on older Mac, but not really because I come from core network side, so I have some idea of all this. So that's why I chose this Meetup. Well, it's actually is interesting in that one of the key use cases that we go after. So so one of the core use cases. So VPP was originally designed for, let's say, network, pure packet processing applications, things like virus router, things like customer pricing, those kinds of things. What we're trying to do is we're trying to scale up also to enterprise, cloud, storage, all kinds of devices. So enterprise is one of the use cases that we want to add. And we've added specific, making it more container friendly as one of the ways in which we're making research for enterprise are two of the priorities this year. So look, take a look at VPP and see if it helps you use this. See if it helps you use it. Because it can never be it's one of the priorities for this year. And a lot of the work that we've been doing has been enabling it to scale down typical enterprise use cases. Things like customer pricing, where you might more VPP as customer premise, maybe talking people POE back to the core network, those kind of use cases, acting as a firewall, acting as just a DHCP server, acting as a matching, those are we've done work on all of those this year, specifically for enterprise use cases. But the other people, they want to optimize, they want to say, hey, all that logic that's in the branch office or the district office today, I want to pull all that back into the core network. I just want a simple switch. And so what we do is we enable vCPU as well. So where you can have customer this kind of branch off it, and then you pull out logic and again, in the container or virtual switch, servicing in the cloud. So all that kind of stuff. Does that make sense? That's for, don't cause offense, because the software guys worry the whole time that the hardware guys are going to be in control. So look, what I think we're going to end up, it's going to be a long time to come, but we're going to have a hybrid future. We're going to have to realize the benefits of it. Because there are other cases where it's going to make sense to use it. Before is exactly right. How do I express my normally express my software? I express my this part of the problem is software and this part of the but that interaction is always on. That interaction is in the future. We're not there. Need some time to mature, definitely. I have to catch a flight. I'm catching a bit clear feeds, but this, if you're interested, please do that. Thank you so much.
Okay, never mind. That's what I was looking for.
Thank you so much.
Edit go Brown. Thank you.
I'm sorry?
Edit go Brown.
Oh, Aaron McGraw. Gee, that was, that's, last time I read that was in the book, Star of the Sea.
No, but I remember, because I went to Shannon one time.
You went?
Yeah.
Oh,
So.
What portion of Shannon?
Oh, we had a delayed flight, so they took us over there.
No, really?
Yeah, that was my introduction to Shannon, Ireland. So have a good flight.
Myself and Christian are both based in Shannon.
Okay.
Christian's staying, unfortunately, I have to run. But yeah, it's actually very convenient for the airport, but we do end with a lot of low-flying planes over the building, rattling our windows.
It was good to, I have voice and I would check you out. I'm Shannon. Oh, okay.
And who do you work for?
I work at a cover check accelerator that helps U.S. military veterans transition to an iPad.
Okay.
So it's just good to hear your voice and I go, oh my gosh.
So that makes a lot of sense because we do a lot of military flights. But a lot of military flights go through Shannon. Like when you're catching a flight in Shannon, there could be a whole crew of army crew around you. Listen, welcome. And you're working for Empower.
Like I told you, the U.S. military veterans.
Oh, okay. So you work Empower is in the UK. Empower is in the UK. They're the national power grid. That's it. I know these things. Thank you. Did my presentation make any sense?
A little bit. For me, I'm still a novice. Oh, okay. Thank you.
Sure. Well, in theory, if you're using
a number of
in theory, you shouldn't have to end. In theory, you shouldn't have to end, but use the low ELD preload layer transparently. That's my preference. Who do you work for? Oh, you work for Cisco? Okay. So in theory, you should be able to just use the LD preload layer and then continue as nothing has changed. Right? And now the question is you're going to get a performance scope out of that. The question is where do you want to go next? So if you want to get more performance, then would you require you to? Okay. If you want to realize more performance, well then you can have the VCL library then where communications like the library. And what that will do is it has what is called socket library on API, except it changes the code and selects the language where you're or something that's for something that scales that, right? So, and that's really, so the electric preload there, in theory shouldn't have a chance of, but again, if you want that additional work and performance, you can change up the, you can change the,
While we're waiting for
everyone to come back, I want to remind you guys to fill out the survey. We're going to be doing a drawing for a Kindle Fire after at the end of the meetup. So the survey can be found at surveymonkey.com. There's a /R and then another / and it says August meetup. I posted the link on the meetup, the out of the box meetup page, so you can go in there and you'll see that it's in the comment section there. So please do fill out the survey, let us know how we're doing, let us know what topics you guys would like to hear about.
Yeah, so we'll get started now. If people outside can hear my voice, please make your way in. So we're starting with the next talk, NFV and SDN, Architecture and Optimizations for the LTE and 5G Wireless Network. The presenters are Krishna J. Murthy and Sumesh Subramaniam. Krishna Jambur is a network software engineer working in Intel for 12 years with experience in working on network processors, Linux kernel, real-time virtualization, Intel microarchitecture performance optimization, multi-access edge computing, and containers. He's interested in the low latency real-time system designs, 5G access and edge cloud, hardware offload, and data plane. Sumesh Subramaniam is a senior wireless software engineer working in Intel with 10 plus years of experience in wireless technologies on custom ASICs. Currently leading FlexRAN software program and focusing on L1-PHY implementations of 5G and 4G networks on Intel architecture. So, the floor is all yours.
You guys can hear me? Okay. So good evening, everybody. My name is Sumesh Subramanian, and I have my colleague here, Krishna Murthy, who will also be talking. So we are sharing this 1 hour period for talking about what we are doing in the wireless space. So both of us, we work in Intel. We've been around 10, 12 years in this this company. So we work for the DCG group, which is a data center group, specifically under NPG, which is Network Platforms Group, 5G ID, which is 5G Infrastructure Division, and Software Wireless Access. So today, mainly, we're going to be talking about software wireless access. So maybe can I get a show of hands of how many people understand what wireless access space is? Okay, that's quite a few hands. Okay, so when we say wireless access in our group, we are not talking about Wi-Fi or Bluetooth. We're basically talking about the 4G and 5G networks, right? What your service provider is giving you as connectivity. So this is what mainly we're going to be talking about. So I'll be talking about, I'll give a brief introduction into the wireless systems, and then also talk about our FlexRAN system, right? And then Krishna will take over and talk about NFV and SDN and what we're doing in that space, and also talk about MEC, right? And then we'll go into our demo and our live demo and what we have today in Intel for this wireless space. Okay, so this picture, this is aimed at basically giving a very high-level view of what is happening in the wireless world, what is happening traditionally and what's coming new to the market, right? So over here, I basically plotted out what is the wireless core and what is the wireless access, right? So in the wireless core, you have this entity called the EPC, which is the Evolved Packet Core. It's basically the entity that's facing the internet and then and the other side is facing the wireless domain. So it's responsible for getting all the data from what the user is requesting from the internet or from the private network or whatever, right? So this entity is usually maintained by your service provider, and it's sitting in their core, right? And then there's this new concept called MEC, which is mobile edge compute. So where a lot more workloads are being taken away from the data center or from the internet and trying to be moved closer to the edge of the network, right? So this is a very new kind of thing, and people are trying to deploy this. And then finally, you have the eNode B system, which is your base station, right? So typically, there are multiple eNode Bs talking to the EPC, and your eNode B is usually towards the edge of the cell. So, yes.
The official name is multi-access.
Right.
Not mobile anymore.
Exactly. Yeah. So there are multiple names. Yeah, but you're right. Yeah. So he just pointed out that MEC stands for multi-access edge compute, right? Yeah. And then finally, the eNode B system, which is your wireless base station, which is giving you connectivity to all the users that are connected to the eNode B. And this is closer to the radios, right? So this is at the very edge of the network, right? So this is how a traditional network looks like, and then this is what is happening new to RAN. So there's one disclaimer. So the wireless world is pretty notorious with abbreviations. There are tons and tons of them. So I think we are going to share these slides with you guys after the presentation. So we have put up a glossary with most of these abbreviations. So, and we'll try to expand on most of them, right? So RAN basically stands for Radio Access Network, and it's basically the eNode B. So there are multiple names for the eNode B. It stands for RAN, ENB, eNode B. People call it in many names, right? So what is coming new to RAN, right? So what people are saying is, so traditionally, again, this is sort of centralized. The EPC is a centralized function. It's sitting in the service provider's core. And then the eNode B is all sort of distributed. It's sitting next to the radio heads, right? So now what they want to do is try and centralize some or most of the eNode B functionalities into a data center, right? And then drive only the radio traffic towards the radios, right? So with this, you can do a lot of different things. Like you can do small cells of mini cloud RAN, all these kinds of deployment scenarios are possible, right? And I'll go through a few more slides as to how this is helpful. But this is what is new to RAN, right? So this is how the network is evolving, and this is what the service providers think they want to be doing. Yeah, and like Ray mentioned, we would like this to be interactive. So if you guys have any questions, just yes.
I have a question. You're showing MEC north of the Sierra.
Right.
There are a lot of talks about having base stations next to radio heads.
Right.
So what's your opinion? Where do you see it coming?
Right. So Krishna is going to talk more about MEC. So yeah. So the question was, I guess the MEC is going to be close to the base stations, right? And then we are also saying the base stations are going to be close to the radios. Yeah. So Krishna will be talking more about MEC, but yeah, the idea is to have the MEC close to the eNode B, right, or close to the RAN, so that you can offload most of the traffic, or you can build apps on the MEC infrastructure itself. So this reduces latency, right? You don't have to go all the way to the internet and then come back.
Now, what you are showing is 15 kilometers away over C3, right?
Right.
What being talked is being within meters of connectivity.
Right, but the CIPRI is, although the CIPRI is far away, you still have to meet your 1 millisecond latency and things like that with your eNode Bs, right? So you're not going to be adding a lot of latency to the CIPRI itself. But since this guy is going to be sitting next to the eNode B, he does not have to go, if you have an application, or if you have a user that's getting some application, let's say from YouTube or something like that, right? It needs to go through a lot of hops, and by the time it comes back, there's a lot of latency. Right? By caching some of that YouTube content, I'm just giving an example, right? In an MEC kind of thing, you avoid going all the way to the end of the core and then come back, right? So those are the kind of applications that people are talking about. Yeah, does that answer your question?
No, my comment that you're showing is too far away.
Right.
It's actually much closer to the
Right, it is. I mean, I guess it is close to the eNode B, right? I guess this line is wrong, but I mean, there's not a lot of distance between the MEC and the eNode B itself. It's right next to it, right?
EBU hotel is in general in radius of 15 kilometers from radio heads. So you're 15 kilometers away from the head. Which is significant.
Right. But again, we are saying that the eNodeB functionality is pretty close to the MEC, right? So in this picture, don't look at this picture, but in this picture, the MEC is going to be sitting probably in the same data center as the eNodeB. So it's going to be right next to it. Right? And then you're driving just radio traffic over simply to the radio. Yeah? Okay, so this slide is talking about the deployment evolution. So again, so the EPCs today are sitting in data centers. They are running on Intel architecture, right? And then you have Ethernet backhaul for all of your IP traffic to your cell site where your eNodeB is running, right? So you have layer 1, layer 2, layer 3, transport network layer, all of these things sitting right at the cell site, right? And typically, traditionally what people have been doing is they have custom silicon, custom SoCs for the eNodeB functionality itself, right? And then the next generation networks, what they are saying is they want to try and take out this eNodeB piece from the cell side and try and move it closer to the data center, right? So you have more workload in the data center, and you just have to transmit IQ samples of radio data all the way to the edge of the cell. And so what does this help with? So with the custom solution, obviously you have a lot of CapEx, OpEx. You need to build something specific for the network. With this kind of solution, when you move things to the data center, you want to run these kind of applications on COTS hardware, right? So already there's a lot of investment in the data center by the service providers, so they want to try and run these functionalities here. And it also, you can make use of virtualization and other IT deployment things that are already available out there into this kind of wireless space. So this is what people are thinking, right, in terms of deployment. And because of this, the network is also evolving, so the standard bodies are also evolving. So what I'm showing here is a deep dive of the RAN, or the eNodeB itself. So if you split it out into these blocks, so all these blocks here in green are part of the eNodeB itself. So you have this RRC entity, RLC, MAC, and PHY. And then there's the RF here, and then the core network on the other side, right? So, sorry. Yeah. So the RRC PTCP is an L3 functionality, MAC RLC is L2, and then the L1 is basically the PHY, right? So when I take an example of today's network, let's say a 4G LTE network, and I take a 20 megahertz 2x2 cell, the throughput, in ideal conditions, when the channel condition is awesome, the throughput coming all the way from the EPC to the user is in the range of 146 Mbps at this interface, 147 at this interface. All the way here, it's around 2 Gbps of traffic, right? There's a lot of data being transferred at the file layer itself. And then in terms of latency, you can tolerate within 100 milliseconds of latency between these two interfaces, and by the time you come here, it's in sub-milliseconds. So this is your 4G network today. And with 5G, what's happening is this number is going up. It's in the order of 10 Gbps and stuff, that's what people are saying. And this number is coming down. It's going to be like 0.2 milliseconds at multiple standards coming down. Oops. Yeah, so there's a lot of complexity that's growing, and then there's much lesser time to do all this work, right? So 5G networks are getting more and more complex. So again, reiterating the previous slide, we have the core network, and then this entire stuff is running right at the edge of the cell, right? So this is what is called as a distributed eNodeB kind of deployment. Now, the standards have started evolving, so what they are saying is you can start splitting all these layers with all of these kinds of latencies present, and then try to centralize move most of these things towards the EPC, or sort of not towards EPC, but try and centralize these things, right? So you have all these different kinds of splits where you can split the PTCP. The data moving here is still, some kind of proprietary APIs and whatever, but they want to try and split these things, right? So so the service provider now has a choice. So they basically can choose one of these kinds of splits and figure out what works for them in their network and try and deploy this, right? So what we're trying to show here is with this kind of thing, building an ASIC or application-specific processor for each one of these models is probably not going to be feasible, right? And if we do all of these, if we can support all of these kinds of things in software, you have the same kind of a hardware platform, and you can run all of these kinds of modes, right? So that's where Intel is driving, right? So that's where we in SWA are trying to say that, okay, we can sort of prove all of these kinds of modes, and then the end customer can pick it up and try to do something with it. So, yeah.
So split means you're splitting the left-hand side functionality onto basic and the right-hand side?
No.
What is the split?
Right. So the split here literally means that these functions can be separated away from these functions. Right. That's what we mean by split. So they could be sitting far away and these could be sitting far away.
Like
but physically, right? But the problem is you will start having problems with these kinds of things, right? The latency, the tolerance here is 1 millisecond. So if you keep it really far away, you're not going to have a good link, right? So there are challenges, obviously. If you go to a split like this, you can't go too far away. You probably have to be very close to each other. But yeah, so what we are saying is you don't have to build a custom solution for each one of these models, right? Yes?
And you're not splitting, you're splitting the entire box, it's not partially, right?
Right, exactly, yeah. Yeah, the functionality within those boxes.
Can you repeat the question?
Oh.
Sorry.
So the question was, are we splitting parts of this box or the entire box? So the standard has defined functions within each box, and that's what can be split.
In the Cloud Run architecture, the big problem is the latency between the RRU and the BBU.
Right.
So is there any dynamically change between these dividing to, for example, if the bandwidth is low, so can we use the physical network function increase capability?
Right.
Or can we choose how can we split it?
Yeah, that again, so let's say you split at this layer like this, right? And you put some software-defined piece even towards the RF, then all those kinds of things are possible, right? As long as it's software defined. But as soon as you put something specific, let's say you're running only layer 1 towards the RF, then it's very hard to bring in layer 2 if you want to, right, based on demand.
Yeah, but what I know that maybe I'm wrong, but the big problem is in the Cloud Run, there is no definition with how to split architecture. So is there any working progress on it? So how we split the architecture layer by layer?
Right, so what we are doing is we partner up with a few other companies, right? So there are certain companies who have such blocks here, and they have very good split within those layers themselves, right? So what we try to do is, let's say they have Ethernet protocol between these two, and they have some special APIs themselves, right, to communicate with each other. So we try to split them apart and try to see if we can communicate over Ethernet, right? So there are a few splits, like we work with certain service providers, for example, they want this kind of a split, right? So in our group, at least in FlexRun, this is what we're concentrating on, this kind of a split, right? But there are also certain questions where people want to split here and see how that works out, right? So yeah, we are trying to address all of these things, but it's based on what our customers are asking us.
Okay, thank you.
Okay, so that was just a very high-level overview of what is happening in the wireless space and how it's evolving. So next we will go into FlexRun, right? What exactly is Intel doing in this space? That's what these set of slides are going to talk about. What exactly is FlexRan? So it stands for Flexible Radio Access Network. So in a gist, it's just a wireless base station running on IA. That's what we mean by it, right? So as soon as we say running on IA, you get all of these things like scalability, flexibility. It's a software platform with optional hardware acceleration. You could put FPGAs on PCIe cards and accelerate certain functionalities, right? And yeah, so all of these kinds of things are possible. That's why we call it flexible, right? So what exactly is this? So what we are doing is we pick up a standard COTS hardware. It's commonly off-the-shelf available hardware. So like one of the platforms that we are showing here in our demo. And what we are doing is, at least in our group, in my group, we look at the layer 1 piece. The layer 1 piece is probably the most cycle-intensive and MIPS-intensive part of, again, getting a 15-minute warning. Yeah, MIPS-intensive part of the entire RAN functionality. So we are trying to optimize that into IA and provide that as a solution to our partners and customers. So they can use these optimized functions and plug it into their, their software and try to see if they can port it as well, right? So we build a reference software. And then on top of this, we also define the operating system, right? Like I said, wireless space is a very low latency kind of thing, right? You're talking about sub-milliseconds and a lot of throughput and stuff like that. So we work very closely with our Windrover team, and then we feed in a lot of inputs and try to reduce the interrupt latencies and things like that to help us make these workloads possible in IA. So again, by doing something like this, you could run a RAN, which is your layer 1, layer 2, layer 3. You could run the EPC, which is all of these components, or you could also run an MEC kind of an application, right? So for an operator, he just has to buy a rack and then deploy multiple VMs, or run the same kind of workload on the same VM, stuff like this, and it's the same platform, but he can run different workloads, right? So that's what we are trying to do. And then at the other end, you have these RRHs, radio heads, right? Typically, there's a protocol called CIPRI, which is Common Public Radio Interface. So most of our radio heads follow this protocol. So we have FPGAs that are connected over Ethernet. So this FPGA is basically converting Ethernet to CIPRI and so on, right? And in the future, moving forward, there is something called radio over Ethernet protocol that's coming to these radio heads itself. So it's probably going to be just an Ethernet interface going all the way to the RRH. Right, so in a gist, this is what FlexRAN is, right? So this is what we are showing also in our demo today over here. Okay, so this diagram is talking about the layer 1. So again, in my group, we work on layer 1, so we wanted to show what exactly are the challenges, right? So this is a typical flow of data in the layer 1. So this is downlink, meaning data moving from the eNode B to your device, right? So there are all of these blocks. And then this is uplink, meaning data coming from your device all the way to the eNode B, right, the other direction. So there are many, many blocks here that are very, very cycle intensive. It's not very easy to run all of this in 1 millisecond TTI and things like that. So what we also do is we offload certain things to FPGA. So we work with our PSG group, and we try to offload certain functionalities into FPGA. So these are called the front-end pieces. Again, if you remember from the slide, these are part of the lower PHY, right? So the throughput at this interface is around 2 Gbps. At this interface, it's around 1 Gbps, right, per antenna. So, so the throughput also reduces, and you remove some complexity also towards the radio head. So again, a lot of our customers are asking this kind of a thing, right? So we work on these kinds of things. And also, there are two other blocks, this turbo encoder and turbo decoder. These are bit operations, very, very cycle intensive. There are a lot of loops, a lot of iterations, right? So again, in a traditional device, even in a DSP kind of a thing, they build hardware accelerators for these, right? They don't just run it in your DSP. So again, what we do is we're trying to take some FPGA and try to offload these things. There are a lot of customers asking us to do this. So we call that a look-aside FPGA. So it's basically a PCIe plug-in card, and we try to offload this onto that. And then my final slide. So this is what we are doing from a FlexRAN to help our ecosystem and partners, right? So we define the platform. So today we are running on our current Xeon platforms, and then we also work with our FPGA group to define IA plus FPGA. And we also feed into our next generation Xeon processors as to this wireless workload, so they can build some instruction sets and stuff like this to enhance, right? So we will be capable of doing wireless workloads more efficiently on IA. And then from a software perspective, we do provide drivers, platform support, framework, which is the BBU pooling piece, all of this kind of SDK kits. So again, our customers can pick it up. They might not want to use our entire FlexRAN solution or 4G or 5G solution. They might have their own magic recipe, right? But we provide these tools and also this SDK with these optimized functions, like things like IDFT, IFFT, FFT, which does not have any magic recipe, right? We provide these to our customers and enable them to get to market quicker. So that's one of our things. And finally, the LTE releases, right? So currently we have a complete 4G 3GPP release 10 compliant software running there. And we are also looking at 5G-TF and 5G-NR, which are the new two standards coming out, one driven by Verizon and one driven by 3GPP itself. So we have started doing some work in these spaces as well, and we are providing optimized spec. Then we have a group where we have an end-to-end kind of a demo with 5G in our labs, but it's very rare. We can't just bring it over here. So we're showing a 4G demo here. Yeah, so these are all the slides I have. So.
Do you want to take a couple questions? Or?
Yes, exactly. Yeah. So if you guys have any questions. Yeah.
Where do you expect money to come from?
Sorry?
Obviously, you want to sell hardware. You know, run is a killing business, sometimes single-digit margins. What are you going to sell besides hardware?
That's a good question. Yeah, it's mostly hardware. Right? So Intel is all about hardware. So what we are doing is we are not selling software. We are enabling our customers by building reference solutions. So our charter is two-tier. We do these kinds of POC kind of things. We go to the operators and say, hey, we have a working solution in IA. Right? And then we work with our partners and other tier 1 customers to enable them to go to.
So the expectation from customers is to get software for free, just as enablers, infrastructure.
Oh, yeah, for us, yeah, I mean, we just give it for free. Yeah, there's a license, of course, there's an NDA license, but yeah, we would like it to run on IA, right? So that's pretty much our requirement.
Okay.
Any other questions? Okay, so I think I'm over. Okay, with that I'll hand it to Krishna, and he will talk about the next few slides.
Okay, so we will now look at some of the wireless use cases. So we looked at the FlexRAN architecture and how challenging it is, and we now need to understand how do we address these challenges and still show our NFV use cases and still show the typical gains from SDN and NFV deployments. So the kind of work that we do in enabling customers with virtualization and SDN use cases are broadly classified into these 3 groups. So we enable customers to transition from custom silicon or custom hardware to Intel architecture and help them achieve higher performance, right? And we also develop proof of concept which demonstrate effective platform utilization, because from ASIC world, they are sort of dedicated hardware which cannot scale. That's the biggest one of the biggest disadvantage with ASIC. And what we are showing here is that on a Xeon multi-core environment where there is plenty of cores, I/O and memory bandwidth, how do we effectively utilize and still achieve flexibility? And lastly, develop optimizations for infrastructure. See, at the end of the day, when customer wants to deploy a base station in virtual machine, they need to find a path such that whatever data is coming today through the network reaches them quickly and deterministically. So if the path is bumpy or having a lot of issues, then that's one of the demotivating factors. So we try to address those blocks or challenges in NFV infrastructure, because some of the things that we saw when Ray presented, there are certain network elements that can take advantage of classical Linux KVM infrastructure. Then you start putting these real-time ASIC workloads in a virtual machine, the challenge completely amplifies. And we are trying to address that by optimizing the NFV infrastructure so that customers don't need to go through this, but rather think and work about their workloads. So going back to this diagram that we showed earlier, so we will look at some of the challenges and what the solutions that we developed, right? So why would customer typically want to move to IA? One of the reasons is densification. Consolidating the stacks, having most of their workloads in virtual machine, and also in a sort of a densified platform such that you have higher gains by deploying such solutions. So one of the challenge here is that you have virtual machines, each having their own characteristics, and then we also saw this split, and even with that split, we saw that some of the components on the right-hand side were packet processing oriented. Some of them on the left-hand side were real-time, low latency oriented. So when you have these virtual machines here, for example, L1 is latency, L2, L3 is again latency plus packet, and you have your transport. This is your TCP or IP stack, and then you have your apps. So each of these have different characteristics, and now you start consolidating on a single server or single architecture, you start seeing challenges. And we try to demonstrate this through various mechanisms. We use platform enhancements, so we get to understand the issues from customers and try to incorporate them in silicon and then expose it through Linux KVM. So some of the standard things that we have done include Intel RDT, which is resource directed technology, where you can separate cache, separate memory bandwidth, so that you can achieve deterministic performance. Second is efficient utilization of resource. So having multi-core is one thing, and you want to use those multi-core in an efficient way. For example, you have your layer 1, and all of a sudden, for example, let's say there is a game, and that base station is experiencing higher bandwidth. Now you want to allocate more cores or resource to this virtual machine for that duration, and then remove the resource and allocate it to somebody else or shut it down to save power. So what we call as dynamic resource allocation is one of the use cases that we work on to demonstrate, still by achieving all those latency numbers and all those throughput numbers. So scaling, flexibility, still meeting all your LTE and of course the 5G performance requirements. Next is the deterministic execution. So any event that happens on the platform needs to be delivered to virtual machine as quickly and as deterministically as possible. This includes timers. For example, somebody does a delay or a sleep, and then he needs to be woken up deterministically, because if he wakes up with higher latency or what we call as jitter, then he misses the entire processing deadline. So we make sure that all those platform events reach the user space where the workload is actually there, and he can execute the rest of his job. Lower latency for VM to VM communication. So we look at the splits, and we also saw other splits in previous slides. So once we have splits, that means that there is also a requirement for east to west traffic. That means L1 virtual machine wants to talk to L2, L3, and which ultimately wants to talk to transport layer, which will send out the packets, which will be consumed by your apps. So what we call as east to west traffic, and we need to make sure that they are deterministic. We don't have bottleneck with, for example, vSwitch and interfaces. So we work on optimizing not just the software components like vSwitch and vHost, but we also work on optimizing the Intel network cards and switches. So deterministic VM live migration. So once you achieve this, the next challenge that typically operator asks us is, so for example, we want to consolidate all the network elements that are running on multiple chassis to fewer, for example, during night time, and then spin them up or bring them back to their original status in the morning, right? So for those cases, typical data center mechanism is live migration. So without bringing the cell down, you want to move the virtual machine from one platform to another platform. So we have demonstrated that using higher layer protocols. L1 is challenging because there are still a lot of signaling happening even though the users are not connected. So we have demonstrated that this mechanism of live migration of higher layer base station layers, for example layer 3, across platforms with VM downtime which is far lesser than what you see in data center today. And of course we have SDK for apps development, which we'll go through. The last one is So ultimately, at the end of the day, you want to have deterministic end-to-end latency. So there are certain things that Intel can do on the platform and the infrastructure, and there are some things that we need to work with our community. And we are trying to make sure that there are no bottlenecks here on the solution space on the server side and also on the IO side. So we are working with operators and telecom equipment manufacturers to see how this future interfaces can help us enable such deployments. In the next slide, we'll look at the use cases and looking through the lens of our FlexRAN architecture. On the top, you see the end-to-end pipeline of FlexRAN, right? So, which we saw earlier, you have remote radio heads, and we have a front-end device that terminates this wireless streaming protocol called CIPRI and converts it from time domain to frequency domain, and then also does some amount of layer 1 processing, and then sends the packets to our servers. So the server is here now. So, and within the server, we have demonstrated virtual machines for base station where L1, just L1 is in separate VM compared to L2, L3, and or a mechanism where the entire L1, L2, L3 is in a single virtual network function. So the optimizations and the use cases that we have done are reduce platform latency for 5G. So we take this DPDK as the base and try to make sure that if customers start using this DPDK to build the base station, they have a better mechanism of getting packets, because DPDK is pole mode driver. You would like to have deterministic packets, because doing vector processing or burst processing is good for most of the packet processing workloads, but for real time you need to be aware of certain things that you need to take care of. So we make sure of that, and we look at how do we reduce the overhead on CPUs so that the CPUs will be available for customers to do their packet processing by, for example, we offload certain parts of vSwitch and pre-classification for MEC onto the NIC, which is Intel Network Interface Cards, which has flexible filters, so that when the packet arrives, they can arrive in such a way that they are automatically load balanced or distributed across multiple queues. So the workloads can start using those packets from those queues, which means that they have better cache efficiency, then you get better performance. Next is the scaling, which we talked about, which is dynamic resource allocation. We have mechanisms where the FlexRAN stack that we have developed can add cells dynamically and remove cells dynamically, which in turn makes removing of cores allocated to the virtual machine, which is also dynamic. So ultimately this means that we can save power and we can also load balance the resource on the platform. So along with virtual machine deployments, we also look at container deployments. We are evaluating multiple architectures. We don't want to put a huge virtual machine in a container just for the sake of containerizing it. So we need to look at what is the real architecture split and gain, and then start containerizing those sort of modules, or what we call as microservices or RAM. So once we do all these enhancements, we also want to make sure that these enhancements are exposed to the higher level orchestrator and OpenStack. So we do that by working and exposing those APIs to OpenStack. We are also working with multiple orchestrators so that these enhancements are available for customers to sort of orchestrate a FlexRAN-like solution. Lastly, the live migration use case that we mentioned, so that we can migrate the virtual machines between platforms to achieve consolidation. So most of these use cases that we work, we make sure that they are available as close to commercial solution with Wind River Titanium Cloud, and also we make sure that it is upstreamed through OP/NFV projects through KVM for Linux, where we have a real-time work group and all these optimizations are upstreamed. So lastly, we also make sure that we use the FlexRAN for end-to-end test beds, both for validation and demonstration. And we have one here today, we'll go through that. So looking a little bit deep into the NFVI stack and how it looks. So we have today, we use Wind River Titanium Cloud 3, which is a carrier grade network environment. And following are the important components that really enable us to run layer 1 like workload in virtual machine. That includes like the real-time extension, low latency and carrier grade. We also have this is the requirement from the stack itself. So if you don't meet your timing, then your eNode B doesn't even work, and the users can't even connect. So we have near native performance. That means when you virtualize your layer 1, the performance difference from running this workload on bare metal Linux compared to virtual machine is it's nothing today. So we have optimized that in such a way using both the Wind River Linux environment and also the enhancements that we have in the silicon. So this includes near native performance for interrupts and whatever we call the infrastructure events, and also the stacks. We also have multiple cell support. We can run a single cell in a single VM, or go all the way up to, for example, 8 cell in a single VM, and also we can run 2x2, 4x4, and in whichever sort of dimensioning that you would need. And we also optimize data path, and that would also be a sort of a reference for customers. And how do we handle packet forwarding and pre-classification for both RAN and MEC? So this, the architecture for NFVI is same, and this enables us deploying both base station along with our MEC applications. So these MEC applications, if they are closer to the base station, then they can take advantage of multiple things, which are like, for example, user information and what we call as RNIS, which is called radio network information. So the apps being closer to the base station can service the users more intelligently compared to the same apps being in data center. So lastly, because everything is implemented in software, it can scale all the way from Atom to Xeon, and even within Xeon, it can support Xeon D, Xeon SP, and Xeon EP. So the infrastructure also supports mechanisms to offload to an FPGA, which is again visible through your OpenStack. So the infrastructure is today ready for deploying such solutions for 4G. So in order to achieve this sort of performance, we had to do a lot of optimizations. And these optimizations means that we need to use a lot of tools. So Intel has a very rich set of tool sets which enables customers to understand what is the current performance, where is the bottleneck, and how do we address that. So some of the tools that we used in FlexRAN include the vTune amplifier and inspector, which analyzes where is the hotspot in our stack and then try to address them so that you see better gains. And then we also use math kernel library here, which has some of the DSP functionalities which are provided to you out of the box. We also use Intel compiler ICC because this enables us to use instruction sets like AVX 512 and AVX2 to implement some of the low-level math algorithms like IFFT and IDFT, IDFT. The tools also has a mechanism for taking advantage of multiple cores by doing multi-threaded programming. So TBB is such a framework which is available out of the box. We use, in FlexRAN, we use DPDK based architecture, which is mainly pthread based. So let's switch our attention to MEC, which is multi-access edge computing. We have an SDK, Intel provides an SDK for operators and application developers to kickstart the application development and also do some trials with MEC. So we call that as Network Edge Virtualization SDK. So we have gone up to 3 releases now with this SDK, starting from Atom, and today we are supporting Xeon and Atom. We provide out-of-the-box eNodeB and EPC environments using Polaris emulator. And we also provide tools. And so we basically provide a sandbox here where the entire infrastructure is ready for an application developer to just drop his app into a virtual machine. And once he does that, he gets all the interfaces that HC MEC defines. And this includes REST API. So for example, a video transcoding application here can request for resources, request for what the standard MEC interfaces that are defined by HC, and he can get it. So the SDK itself makes it transparent such that MEC can be deployed on S1 interface or SGI interface. We support VLAN, and we also support complete OpenStack environment. For application developers who don't want to have this setting up the complex OpenStack environment, we also have a small footprint CentOS based environment where the requirement is just a single DPDK port so that you can get all the traffic. So if we look at the, so we closely use the HC MEC architecture to do this. Yeah.
You have a solution to mobility events in MEC, synchronization between different. Do you provide a solution in case of mobility event between NECs?
Yeah. So mobility event in MEC is one of the challenging aspects. So the question comes here is, for example, you have an app and which is being serviced by a particular eNodeB. So you have a user who is trying to use, for example, an internet service, and it is going to an eNodeB and it is going to a MEC app. And that user moves and the eNodeB handover happens. So how is this handled by this MEC app? So the path that we have taken here is we want to be as close as possible to what HC MEC defines. So the interface for handover for HC MEC is they don't want to define it. So there can be a custom interface because there are things like N-to-1 or N-to-N interface. For example, N number of eNodeBs can be connected to a single MEC platform, or multiple MEC platforms can be connected to a single eNodeB. So depending on such deployments, it's up to customers how to handle these mobility events.
But you see, that's the problem, right? There is nothing in definition, and you need to optimize. If you keep it generic, the time to move to share state, share memory.
Yes. So I think the challenge here is, it depends on how a customer implements. For example, the mobility event that the eNodeB gets can be shared with the MEC platform. So, but this event of mobility, which is for example over X2 interface, needs to be somehow communicated to the MEC app. And this interface is what Etsy doesn't want to define. And they have left it as an open interface for implementation. So handling this in SDK is a bit tricky because it depends on what the T-Node B does. So in this architecture, what we see here is the green blocks that are provided as part of our SDK, which includes OpenStack, data plane. We provide MM5 APIs, which are closed or looks like XCMake because it's just now defined. So, and also we provide MP1 APIs. We also have policy and registration where policies for the apps can be configured and the apps will start using those. Right. So this includes, for example, the mobile edge platform manager will deploy, for example, a UHD app, which is servicing a user with the UHD content. So he will set rules on what users traffic needs to be sent to this UHD app and what users traffic needs to be sent to EPC. So all those can be done using our SDK. So just to summarize, so this is how it looks like with all the components in our SDK. So the orange blocks are the ones which come as part of Wind River Linux. So the blue components are part of MEC deployment. So we develop it on top of DPDK, and we have hardware abstraction. I'll just get to it. And we support S1 interface and IP interface. This is the data plane. And we have an OpenStack controller here, along with the MEC platform manager to deploy MEC apps and also configure policies for them through the service registry. So the first deployment is on S1 interface. This is a MEC box in between eNode B and EPC. So this is S1 new GTP traffic. So we have configuration here. When the GTP traffic comes in, we extract the IP frames and send it to the app. So the app, for example, a UHD app which has been developed, who is looking on a socket, he gets this IP datagram. So it's completely transparent to him, and he needs to just make sure that he calls these APIs. Yeah.
What happens if S1U traffic is encrypted, like in Germany?
So S1U traffic, again, we make sure we follow what XCMake says. So according to XCMake, the encryption is out of scope. So it is understood that the MEC deployment or the MEC apps is somewhere which is deployed next to an eNode B or closer to eNode B or closer to eNode EPC or an environment where it is what they call it as where the security is controlled, or in the sense that what goes into the platform is under the control of operator. So there can be key exchange, or there can be a network element here, for example, transport layer, which decrypts and sends clear text to this MEC routing. So the second deployment is through the IP interface. So you can just even look at this. So this is when you have your eNode B and EPC also. So with 5G to address the low latency, the new trend or new technology enhancement that's coming is also called as distributed EPC. So in distributed EPC, you have user plane of EPC also closer to eNode B, so you get clear IP text packet and we send it to the virtual machines. So this means that we can also aggregate traffic from Wi-Fi interface and also service them, so that LTE Wi-Fi is sort of transparent to the application developers. Lastly, local breakout. For example, let's say this is the UHD app and it's in a VM and he needs a lot of horsepower. And let's say he wants to access some of the graphics acceleration. So in this case, he can configure the data plane such that for a set of users, we get the traffic, and only those users who are serviced by the MEC app, he can automatically redirect it to a set of servers here, which actually does the processing, and they send back the traffic. So this is what we call as local breakout. This also means that you can have your public cloud today from various vendors that we have. can be deployed here. So now we will switch our attention to this demo setup. Want me to go through it? So in our demo today here, we have end-to-end network, LTE network with FlexRAN being the core of our discussion today. So we have a Xeon platform here which runs FlexRAN, and we also have EPC. So, and then we have a drone which is capturing video, so we can switch to that. So the drone, which is here, which is blinking, it's transmitting the video, transported video. So we have an Atom processor here, which is capturing the video from these cameras, and it is transcoding and sending Ethernet samples to EPC. And EPC is sending, the P gateway is sending the traffic back to the eNode B, which is running on the server, which is a Xeon server, Xeon D server. And here we are running FlexRAN. And what we do in this is we are basically doing downlink. So we do all the LTE processing on downlink, if you guys remember what we showed in the previous slides. And then he sends it to a front-end device, which is an FPGA, which is built on Altera FPGA. So the data from here to the FPGA is over Ethernet, right? And from here, he converts the Ethernet to CPRI and sends it to the remote radio head. This is the remote radio head. And from remote radio head, it goes to a LTE user equipment, which is this laptop using the LTE dongle. So we have end-to-end architecture using end-to-end LTE demo using Intel architecture, and there is nothing preventing users or customers to scale this to, for example, to have different splits, or even sort of having in a typical enterprise environment, having both EPC, distributed EPC and MEC app and base station on servers like this. And also, if you can, after this demo, you can also look at the form factor. It is a low profile, single U platform, which has capability to run multiple cells. So, and in this, we are not using any accelerators. Any questions?
You mentioned you have eNode B. It is based on functional split, or for the eNode B, is this based on functional split?
Yeah, I can repeat. So the question is this eNode B based on functional split? Yes, this is the split PHY processing, where a part of L1, which is what we call as conversion from time domain to frequency domain, the FFT is happening on the FPGA, and rest of the processing of L1, L2, L3 is happening on eNode B in a virtual machine. Yeah.
So for the lower PHY, it's after resource demapping.
Yes. Okay, so if there are no questions, thank you very much for listening to us.
Oh, thank you. Don't draw, we haven't had our drawings or idea roulette yet. So.
So who's getting the Kindle Fire?
So did you guys thought
You have to be present to get
you have
the
to be
prize.
present to win the surveys or any of that.
Yeah.
And how we do that?
Huh?
All right.
How you?
Oh, you need to give us the survey. You have to give us
Survey?
feedback.
Where's the survey?
Oh,
It's on SurveyMonkey. So if you go to SurveyMonkey,
Do you have a URL?
yeah, we have a URL. Can we get
Yeah.
see if we can get it showed up. Oh, I got it. Not anymore.
So who got the idea roulette cards? Anybody ready to pitch their projects? Ideas? We have some raffles for people who signed up on Eventbrite also. So for Idea Roulette, we have this DPDK in a box kit. Anyone knows what it is? Okay, I see some nods. Anybody who doesn't know what it is? So it's an Atom processor with two 1 gigabit interfaces. It comes loaded with Linux and DPDK, and it can hook to your laptop directly. So you just power it on and you can start experimenting, start coding. Yeah, there you go. So, yeah, give us feedback.
What is the code for Wi-Fi?
What is the what?
Wi-Fi.
Wi-Fi?
Oh.
Conference and guest access?
Oh, you got it?
Oh.
It didn't work for me, but...
Renee's got one.
Yes?
I've got one too. Let me see.
Just guest?
Hello.
No, it's
The network just give us.
Is it ZZ or...
22. It's all number 2.
I see some people looking at their cards. Is anyone ready to come and talk about their ideas? Or anything they're working on, that's fine.
Grab that team over there. Oh, we got
So what are we going to do? We need to propose a project using these three
yeah.
Or idea. You can just discuss your, what you think about that.
We should sequential with what?
It doesn't work.
Sequential with algorithm.
Hey folks, I'm Ananta from Ericsson.
I'm Prem from Ericsson.
So we work in, at least I work for routing and other IP SDN products. And
I work for the Open Daylight project.
okay, so what we have here is that a combination of SRIOV and integration porting to containers and cost traffic classification. The reason I picked up this is because cost is something which I have done in the past life. Cisco, when I was in Cisco. Meaning, past before. It's been a while, that's what I meant. So what we are thinking is, most of this bandwidth calendaring type applications and other use cases which require, when there is a lot of demand, even in today's thing they were talking about, right? When there's so much of demand, suddenly there is more traffic. In such cases, it should still function properly. So you wanted to put some advanced, QoS capabilities. I design a cost manager, which can be controlled by using SDN type of interface, and that time dynamically dedicate an SRIOE based interface, so that it can things can happen dynamically as opposed to static configuration.
So just to add upon it, the idea is very simple, wherein since this VNF would be based on containers, with the concept of distributed cloud picking up, what's happening is you have compute power available next to the eNode B, and also the ability to host containers needs a smaller footprint. So what we are planning to do is we will probably use the VNF, which is essentially the COS traffic classification, in order to detect the type of application that lands it. For example, if it's AR/VR, you would probably provide a different type of, or instantiate a different type of VNF. If it's going to be a normal mobile phone connectivity, you would probably instantiate a different type of thing. So that's the whole intent. The idea is create a layer or app over it, which would essentially, depending upon the traffic that lands on your eNode B, you would essentially instantiate and then route the traffic to the respective server, which needs SRIOB. So that's in a nutshell.
Just to add a bonus, there is no fun without machine learning. So feed this data to the machine learning node, and it can be more intelligent and try to establish a feedback loop, so that this can be even much more automated. It can even predict not the zero-day attack type of things. What I'm saying is, for in our case, we wanted to make sure it can predict this. Well, buzzwords are there, but we have to do something about it, right?
This is the reality.
Yeah, but just
you need buzzwords to implement all these complicated
right.
stuff.
Yeah, but there is stuff available. TensorFlow is there. Everything. Open source thing is there. We can just integrate.
NFV conference on the studio or struggling with connectivity.
So like someone pointed, it had a lot of right buzzwords there. But as they say, you need buzzwords for a reason, right? For a complicated thing like this. Especially I was talking about network slicing and meeting coarse requirements for variable networks, right? So yeah, there you go.
He needs 2 raffle tickets.
Okay. Hi everyone. My name is Shrikant. I am from Ericsson. Working on the open source Open Daylight project. Sorry. Open Daylight and OPNFV projects. So today I got component as ONOS. So for those who are not aware of ONOS, it is another highly scalable software-defined networking controller that manages various OpenFlow and other OpenFlow based data plane. Then the network function that I got is the load balancing, and the type of project is integration or porting to the containers. So the one that I was thinking of by combining all these 3 things is, today ONOS provides virtual tenant network services for the virtual machine instances. So the first thing, we need to enhance the ONOS SDN controller to provide network connectivity to the container workloads. So the same way that Open Daylight is today providing to the container workloads, ONOS also needs to be enhanced for the container workloads. Once that is done, then the load balancing aspect is, what I was thinking is to implement a disaggregated load balancing. Instead of you deploy a monolithic load balancing in the data plane, you disaggregate such that you deploy the control plane on top of the ONOS controller and implement the data plane using the data OVS switches. So here, few ideas. Instead of just simply keeping it as a network level load balancing, you can introduce some application level intelligence into that load balancer, such that it will monitor the application level traffic and punt to the controller, and controller will make such certain decisions, like based on the amount of traffic or the number of the response time that it is getting from each container. Based on certain constraints, it will recompute the load distribution and re-inject into the data plane. such that it gets more application level load balancing instead of pure network level load balancing. Yeah, that is my idea by combining all these three.
This is the piece that we are concentrating on.
Great.
Exactly.
Wow. ONOS doesn't have container support, right?
Not yet.
Not yet? Okay, that's great.
One more thing.
One more thing, yeah. So that's the spirit of open source, right? I don't know how many were present at the ONS summit this year, and there was a comment at one of the keynotes that the spirit of open source is if you find a problem, solve it. So there you go.
Hello all, my name is Nikhil. I work at Cisco. I don't work with all these three cards ideas anymore because I did some projects when I was in university last year, but my type of project here is adding a new function. The network function is traffic policing and the component is container. From the limited knowledge I know, I want to, so let's say I want to secure the containers or networking between different types of containers. I want to do is like adding labels and policies, like access control list, like what a firewall does for you. So if I have like a front-end container for one functionality and I have a database container for other functionalities, in order to secure the communication between them, I have labels and separate policies for each and every container to make sure the traffic between them is secure. Might be, I don't know how it works in real time if someone has already implemented it, but this is just a small basic idea of like firewall idea which we can use in containers also.
Thank you. Securing communication between containers. Great. Anyone else? Any more takers? No? Yes? Auction, auction, auction. Last auction. Who's taking the bid? No? Okay, I guess it's time.
Time to
Yeah.
draw the DVD case.
Any last bids?
Renee's got the ticket.
Oh.
Yeah. Let me see your call. You need to tear them up and put them here so you draw. No. We're just going to draw right now. No. We'll call it out right now.
We are not concentrating on that because the goal already was.
Okay, that's all. Okay. We had 5 people or 5?
We had 4?
4 with 2.
Okay.
Okay, who wants to draw?
Just choose anyone from the audience.
Here you go. Okay, so the last 3 numbers are 062.
No, this is not it. I'll probably give it to you.
You have one already, right?
I'll give it to you.
So, yeah, draw the other one also, we'll get it together.
That's what I'm saying.
So the last 3 digits are 062?
Oh, that was what we just.
Yeah, that was the one.
That was what we just approved.
Oh, so you should remove that one.
Oh, man. You are so lucky.
The moral of the story is someone wants a prize, have him on the team.
I heard a load balancing.
No load balancing here. Come on. We didn't implement machine learning. You have to do that. Okay. 064. Those are the last 3 digits. Ah, okay.
61.
Yours? Oh, okay.
இது பேசுறாங்கல்ல அதுக்காக
And I need to see the winner before you guys.
Michelle, can you take?
No, you have to write code. No talk. Write code. No talk.
We have 3 in our lab.
The problem is அப்புறம் மகன் வந்துட்டீங்களா மூவ் பண்ணிட்டீங்க
You want a photo?
You can do. Come on.
அதாவது படிக்கிறதுக்கு தான்
I'm part of story.
You're part of the team, right?
You are holding.
planning to move.
Okay, very smart.
Yeah, but she also move.
Thank you.
Okay, so now we have.
Now for the prizes, don't go yet if you registered for the Eventbrite.
Right, and then we have also the Kindle Fire.
Yeah.
So, you have those?
I registered with Meetup. What is this Eventbrite?
Oh, so on the Meetup page, there was an Eventbrite link. So on the Meetup page, some people don't even have their names. So when on the Eventbrite page, we just ask people for their names, for their emails and companies, and they have an option to opt into our newsletter, which just informs people about, what are the activities that we are doing. So if you register for the Eventbrite, there is a raffle for that.
Okay, you did right.
Okay.
And you have to be present, so I'm going to start calling off names.
Okay, yeah.
And we have 3 things. Well, actually, we'll do 3. We'll save them for later.
Okay.
So we've got Power Bricks. And we have this Polo USB hub clock. And we have
Oh, okay. Okay. Yeah, so yes, Starbucks card and the USB hub with LCD clock and mobile chargers. Amit Grover.
Where is he gone?
He's gone.
He has to be present.
Ericsson, you can load
We can proxy.
No proxy. Sorry. Michael Aquino.
Very good.
Again, not present. Jeff Tensura.
He's also.
Okay.
Murat Oh, wow.
All right.
Okay. So what does he get?
So he'll get this.
Okay.
Because we may not have winners for the other one. Thank you. And Richard Vargas. I know Richard's here.
Okay.
Come on down.
So what does he get? He can choose.
Oh, yeah.
Yeah. So do you want a mobile charger or do you want a Starbucks gift card? Okay.
I need another electricity.
Well, that's what I was thinking. Okay, so now we need, okay, so one last thing. It's going to take us just half a second to get the survey.
Okay.
Survey.
Yeah, so just give us a minute while Michelle determines the winner for the Kindle Fire. Everybody given their surveys? Okay. Legit responses? Okay.
Can be machine learned.
I'm sorry, I'm more confused.
In our booth. Yeah, so we are part of the Kindle Fire. I don't know if this FlexPlan itself, what is the timeline for this? So, but yeah, I know we have another product line, another project.
I apologize.
So, by the way, while we are all talking, you should probably know that both of our speakers there, they gave the presentation empty stomach.
Oh my God.
Why?
Yes.
But
why? Why?
Why? Because they didn't want to make us late by eating food.
I thought that's Indian tradition.
Yes, hosts do not eat. Actually, it happened at DPDK Summit in India.
Murat?
Oh, again.
Murat!
Again.
Again, you're a lucky winner for Can Be Fired.
Wow.
There you go. Thank you.
Oh, picture.
Oh, picture, of course.
Actually, let's have everybody in the frame with the winners.
Yeah. And
That's become our tradition now. We take pictures with everybody who stays till the end.
Yes.
No. Everybody.
We want everybody down.
Winners will show their prizes, and others will just. Oh, wait. We forgot. Dharani gets his check.
Yes.
What? Check?
Again?
For village
No. He wanted a picture with it, so he came late, like usual, right? Last time, and he was late again today.
Yeah. He would have had a big crowd see it.
There's a dog, right? There's a dog.
Okay.
By lunch. Okay, and then a picture of everybody.
Picture. Dharani, you can be here with the check.
Oh,
In the picture.
People who won the people who won the
Yes, yeah.
Yeah, and please include your email address in there. I've got some instructions I'll mail you after. I know. Just to make sure it's I look there. So I will email you. So make sure you, please be sure you include your email address. And then.
Yes, it is. The picture is for everyone.
Really?
Yes.
Come.
She wants to see how fast you can break a camera.
What do I want to say?
You want to see how fast you can break a camera.
Yes.
Let's get you guys.
Right.
You guys should join, take a selfie.
Can you guys just maybe on the end just step in?
Yeah, we
just a
can
little bit?
ask him to take a picture.
Don't come here.
You go, friend.
I'm jumbo friend.
Okay, everybody smile.
Okay.
There we go, one more time. All right.
Thank you.
Thank you.
Thank you very much.
So Ron, Michelle, and Rene, you all three also.
Oh, okay.
Thank you. Why don't you come? We can. I think we can.
Stop the stream now. Yeah, and say goodbye to people who are still there.
Shall we all sing a song? Bye.
Bye, everyone. Thank you for joining.
No,
How many core?
No. He'll get an actual
Thing. Ask him. He got one actual thing for December. He got an actual thing. Verify with him. For the December one he got. This is December one? Oh, you got the December one. Okay. Yeah.
And this is how many shot?
Yeah, you got some more.
Oh, wait.
Don't go away. That one more picture.
All right. Oh, one more. Yeah.
Or one key? No, it's 110.
Again?
Yeah, either there. This one. 10.
One more picture.
Oh, one more picture? Oh, okay. Okay.